Somewhere within our galaxy, a stellar remnant, just 12 miles wide, is actively warping the fabric of existence. Its magnetic influence is so profound that it can rupture the vacuum of empty space itself. A single flare from this cosmic object unleashed more energy in a tenth of a second than our own sun will generate over 100,000 years. This is not a black hole, but something that may be even more perplexing: a magnetar. It is an object of such extremity that it challenges physical laws once considered absolute. When a truly massive star concludes its life, a familiar story unfolds. After burning for millions of years by fusing elements in its core and forging progressively heavier atoms, its fuel is finally exhausted. In a fraction of a second, the core implodes. This triggers a rebound in the star's outer layers, resulting in a supernova explosion that can briefly outshine its entire host galaxy. This narrative is well known, but a crucial detail is often omitted. Not every stellar corpse is destined to become a black hole. For stars within a specific mass range, between 8 and 20 times that of our Sun, a different outcome occurs. The core's collapse does not proceed all the way to a singularity. Instead, the process halts. It compresses down into a sphere measuring just 12 to 15 miles in diameter, but it never vanishes from sight. What is left behind is a neutron star, a city-sized orb of matter so extraordinarily dense that a single teaspoon of it would have the same mass as Mount Everest. Yet, some neutron stars are created with a literal twist. As the original star's core collapses, its rate of spin accelerates dramatically, much like an ice skater pulling in their arms. The magnetic field that permeated the star is also carried inward and compressed. Squeezed into this minuscule volume, the field's intensity grows to levels that seem physically impossible. The final product is a magnetar. This is not a theoretical concept, but confirmed science. Astronomers have directly detected these objects and measured their emissions. And the data they have collected is staggering. A magnetar's magnetic field can achieve a strength of 10 to the 15th Gauss. That is a quadrillion times more powerful than the magnetic field of Earth. It is also 1,000 times stronger than that of a typical neutron star. At such an intensity, the magnetic field itself becomes a tangible threat. Consider this scenario. If a magnetar were positioned halfway between the Earth and the Moon, a distance of about 120,000 miles, it would instantly wipe clean every piece of magnetic data storage on our planet. Every credit card and hard drive would be rendered useless. That, however, would be the least of the dangers. The true peril lies in what such a field does to matter on a fundamental level, which is where our understanding of physics begins to fray. At any distance closer than 600 miles from a magnetar, the magnetic forces are so extreme that they distort the very shape of atoms. Electrons, which normally occupy spherical orbits, are stretched into elongated, needle-like forms. Atoms no longer behave as they should, and the basic building blocks of chemistry cease to function in any familiar way. And this is only the start of the strangeness. Imagine the process of crushing our sun down to the size of a city. This isn't a metaphorical compression, but one governed by the unforgiving laws of physics, where every atom is smashed together so tightly that no empty space remains. This is the state of matter within a magnetar. Its diameter is roughly 12 miles, a distance one could drive across in 15 minutes. Yet contained within that remarkably small sphere is a mass equivalent to 4 times that of our entire sun. This figure is not an estimate. Scientists have confirmed magnetar masses by observing their gravitational pull on nearby objects and by analyzing the frequency of their pulses. The results are consistent and deeply unsettling. The mechanics of this are rooted in atomic structure. In ordinary matter, atoms consist mostly of empty space, with a tiny nucleus at the center and electrons orbiting at a great distance. When a star collapses into a neutron star, however, gravity overwhelms the forces that keep atoms apart. electrons are forced directly into the nucleus, where they combine with protons to create neutrons. What remains is a solid mass of neutrons packed together with no gaps, creating matter at nuclear density. This means a single inch of material from a magnetar would weigh more than 600 million tons. A sugar cube of this substance would possess more mass than the entire human population. If one could somehow drop a teaspoon of it onto Earth's surface, it would pass through the ground as if it were not there, punching a hole straight through to the other side of the planet. The density is so extreme that the surface gravity becomes a nightmarish force. An object on a magnetar would experience a gravitational pull 200 billion times stronger than Earth's, a value of 2 times 10 to the 11th. You would not simply be crushed. Your constituent atoms would be torn apart and smeared across the surface into a layer just 1 atom thick. Yet, even this is not the most curious aspect of these objects. Magnetars are not static. Their surfaces can move, crack, and quake. When this occurs, the event is noticeable across the cosmos. The magnetar's immense magnetic field holds its crust in a powerful grip. This crust is a crystalline iron structure, harder than diamond, floating atop an ocean of superfluid neutrons. As the magnetar rotates and its magnetic field evolves, incredible stress accumulates within this solid layer. Eventually, the pressure becomes too great, and the crust gives way. What follows is an event that makes terrestrial earthquakes seem gentle by comparison. On the 27th of December 2004, an invisible wave of energy struck our planet. While it caused no physical impact, its effects were registered by nearly every satellite in orbit. Radio observatories across the globe were overwhelmed, and 60 miles above the surface, Earth's ionosphere was suddenly and brilliantly energized. Researchers scrambled to understand the cause. They traced it to a source 50,000 light-years away. A magnetar known as SGR 1806-20 had experienced a fracture. This was no minor occurrence. When a magnetar's crust ruptures, it unleashes an amount of energy that makes our most powerful weapons seem like toys. The event on December 27 released more energy in 1/10 of a second than our Sun will produce in 150,000 years. From a distance of 50,000 light-years, the flare appeared brighter than a full moon to our satellite-based instruments. This is confirmed data from NASA and numerous observatories. Reflect on that distance for a moment. Light from the burst traveled for 50,000 years and still arrived with enough force to physically affect our planet's atmosphere. If this same magnetar had been located just 10 light-years away, a distance similar to some of our closest stellar neighbors, the resulting wave of radiation would have completely stripped away Earth's ozone layer, bringing an end to all complex life. The mechanism behind such a starquake is what makes it so powerful. The magnetar's iron crust, under unimaginable magnetic stress, suddenly shifts by less than a millimeter. It is a minuscule displacement. But when you move crystalline iron that is harder than diamond and packed to nuclear density, even such a tiny movement liberates an incomprehensible amount of energy. The magnetic field lines, stretched to their breaking point, violently snap and reconnect, like countless elastic bands releasing their stored tension all at once. This event, known as magnetic reconnection, propels particles to velocities that approach the speed of light. As a consequence, gamma rays and X-rays are ejected outward in every direction. The magnetar itself resonates from the disturbance, vibrating in a way that creates pulses we can register from across the galaxy. These powerful starquakes are not brief. They can persist for weeks at a time. Following a major event, the magnetar often releases aftershocks. Each of these secondary quakes can unleash more energy than our own Sun generates over many years. Eventually, the surface of the star settles into a new arrangement, one that is subtly different from its previous state. The entire geometry of its magnetic field shifts. After such a change, the magnetar might enter a dormant period lasting for years or even decades. Conversely, it could fracture once more the very next day, we have no way to predict its behavior. Every magnetar seems to follow its own unique pattern. Some are consistently active, erupting several times within a single year. Others fall silent for decades, only to awaken with sudden and dramatic intensity. Scientists are still working to understand what governs these cycles. The fundamental mystery, however, is what powers this entire process. A critical question remains. Where does a magnetar draw the immense energy required to sustain these events? You cannot perceive a magnetar's magnetic field with your eyes, but its presence is constant and overwhelming. It exists as a sphere of contorted magnetic energy that envelops the dead star. This field extends for hundreds of miles outward in all directions, and its influence is not merely magnetic in the conventional sense. It fundamentally alters the nature of reality itself. At a distance of 600 meters from a magnetar, the strength of its magnetic field reaches approximately 1 billion G. This value has been confirmed through spectroscopic measurements of magnetar atmospheres, specifically by analyzing the cyclotron resonance features within their X-ray spectra. It is at this distance that the familiar rules of quantum mechanics begin to unravel. Consider what this means for light. Under normal circumstances, light travels through the vacuum of space in perfectly straight lines. Near a magnetar, however, light bends. This is not due to the warping of space-time by gravity, but rather the direct influence of magnetism. The magnetic field is so powerful that it affects the vacuum itself, a phenomenon known as vacuum birefringence. Photons passing through this region of space are forced to split into two separate beams, sorted according to their polarization. In effect, space itself becomes birefringent, similar to the way light behaves when passing through a crystal. For anything composed of matter, the situation becomes far more extreme. It is important to remember that atoms are held together by electromagnetic forces. Electrons maintain their orbits around a nucleus because of electrical attraction. A magnetar's magnetic field, however, is potent enough to completely overpower these fundamental forces. The field does not simply pull on electrons, it physically deforms them. Within that 600-meter threshold, atoms are stretched into elongated needle-like shapes. The electron clouds, which should be spherical, are drawn out along the magnetic field lines. The very principles of chemical bonds cease to function as they should. Molecules are unable to form correctly. Complex chemistry, the basis for any living organism, becomes an impossibility. For a living being, this environment means instantaneous death. The cause would not be heat or radiation, though both are present in lethal amounts. Instead, death would come from the fundamental disintegration of molecular structure. Your cells would cease to function long before your brain could even register pain. The proteins that regulate your body would unfold. Your DNA would unravel. You would simply be taken apart at the molecular level. Nothing humanity has ever constructed could withstand this environment either. The atomic bonds holding a spacecraft's hull together would be violently disrupted. Its electronics would fail in an instant, as the magnetic field induced currents millions of times stronger than they were ever designed to handle. Even light itself seems to struggle, bending and splitting as it navigates the distorted space. And all of this assumes one could somehow survive the radiation, which is impossible. Magnetars do not simply rest quietly within their magnetic cocoons. They are incredibly active. The field is not static. It constantly shifts, twists, and reconnects, even in the quiet periods between major starquakes. Each one of these smaller reconnection events sends out its own burst of X-rays and gamma rays. These are not gentle emissions. They are focused beams of high-energy radiation, powerful enough to ionize any matter in their path. Yet, when compared to what the field does to space itself, even this intense radiation seems almost conventional. Light is supposed to be simple. We understand it as photons traveling in straight lines, unaffected by magnetic fields. This is a foundational concept of physics, and it holds true nearly everywhere else in the universe. But in the vicinity of a magnetar, this rule is completely broken. Scientists first theorized this possibility back in the 1930 seconds. At the time, they believed it would be a purely theoretical curiosity. The effects, known as photon splitting and vacuum birefringence, only become significant in magnetic fields that approach or exceed 10 to the 13th G. It was thought that no natural object could ever achieve such strength. Then, we discovered magnetars. Here is what is believed to be happening. In ordinary space, a vacuum is considered truly empty. Quantum mechanics, however, reveals a more complex picture. Even in a perfect vacuum, so-called virtual particles are constantly blinking into and out of existence. Pairs of electrons and positrons appear for infinitesimally brief moments before annihilating each other. While we cannot see this happening directly, its reality has been measured in laboratories through the Casimir effect. Near a magnetar, the magnetic field is so powerful that it polarizes this quantum vacuum. The virtual particles are forced to align with the field before they vanish. This alignment fundamentally changes how light travels through that space. The vacuum effectively becomes a medium, much like air or glass, but one made of quantum fluctuations. As light passes through, it splits into two beams with different polarizations. One beam is polarized parallel to the magnetic field, while the other is polarized perpendicular to it. These two beams then travel at slightly different speeds. This is the essence of vacuum birefringence, and it has been confirmed by observing magnetar spectra. The light arriving from these distant objects displays the exact polarization patterns that the theory predicts. Yet, there is another effect that is even more strange. At even greater field strengths, above 10 to the 13th Gauss, individual photons can actually split apart. A single high-energy gamma-ray photon can spontaneously divide into 2 or 3 photons of lower energy. This is not a concept from science fiction. It is a prediction of quantum electrodynamics pushed to its absolute limit. We have observed this phenomenon indirectly. When magnetars experience major flares, the spectrum of radiation we detect does not align with what we would expect from a simple hot surface. Instead, we see features, dips and peaks in the spectrum that can only be explained if photon splitting is taking place. The high-energy gamma rays are splitting into lower-energy X-rays before they can reach our telescopes. This means that magnetars serve as natural laboratories. They allow us to test the laws of quantum mechanics under conditions we could never hope to replicate on Earth. Our most powerful magnets can achieve fields of perhaps 45 Tesla, which is about 450,000 Gauss. A magnetar's field is roughly 2 billion times stronger. It is a place where physics is tested in a regime we can only dream of accessing artificially. And yet, this distortion of space and light is not even the most extreme behavior that magnetars exhibit. Sometimes, they do not just bend light, they seem to transform it into a weapon. On March 5, 1979, every satellite in orbit around Earth detected something that seemed impossible. A wave of gamma rays and X-rays struck our planet's atmosphere. Its intensity was so great that it ionized the upper layers. The initial thought among many scientists was that it must have been a nuclear attack. The eruption was astonishingly brief, lasting only 1/5 of a second. In that fleeting instant, however, it discharged a greater amount of energy than our own sun generates over 1,000 years. Its source was identified as a magnetar, located in the constellation Norma. The object was approximately 30,000 light-years away from us. It was given the designation SGR 052566. What had been observed was a colossal magnetic flare. It was, in fact, the most powerful ever recorded. The documentation of this event is exceptionally thorough. Data was gathered from Soviet Venera spacecraft and American satellites. Observatories stationed all around the world contributed as well. The phenomenon was so potent that it still holds the record as the most luminous burst of energy ever detected from outside our solar system. Yet, there is a detail that makes this truly unsettling. That immense wave of energy journeyed for 30,000 years across the vacuum of space. It expanded outward in an ever-growing sphere. By the time this energy reached our planet, it had been diluted across a volume trillions of miles in diameter. Even so, it struck Earth with enough force to interfere with satellites and disturb our ionosphere. When one calculates the energy at its point of origin, the figures become staggering. At the moment of the burst, the magnetar is estimated to have released about 10 to the 46th joules of energy. This is a quantity of energy greater than what an entire galaxy of 200 billion stars can produce over several years. It all came from a single object just 12 miles across, and it all happened in 1/5 of a second. The question is, how can such a thing be possible? The prevailing theory points to a catastrophic reorganization of the magnetar's magnetic field. This field, already at strengths that defy comprehension, must have become profoundly unstable. For years, or perhaps decades, the magnetic field lines had been twisting and tangling. They became more and more contorted until the configuration could no longer be sustained. At that point, they snapped. One can visualize this by imagining rubber bands stretched around a sphere, twisted tighter and tighter. Eventually, they would break and recoil with incredible violence. These, however, are not simple rubber bands. They are magnetic field lines, and they carry an energy equivalent to the mass of small moons. This relationship between mass and energy is described by Einstein's famous equation. When these lines reconnect into a more stable state, all of that stored energy must be released. It is channeled into the acceleration of particles. Electrons and ions are propelled outward at 99% of the speed of light. These particles then collide with the magnetar's own magnetic field further out from the surface. This interaction generates cascades of gamma rays through a process known as synchrotron radiation. The magnetar, in effect, becomes a gigantic gamma ray cannon that fires in every direction. For months following the event in March 1979, astronomers were able to detect a pulsating X-ray source at the very same location. The magnetar was still resonating from the sheer violence of the flare. It was sending out consistent pulses every 8 seconds as it spun on its axis. Even after such a cataclysmic release, it retained enough energy to outshine thousands of ordinary stars. This observation gives rise to a rather disturbing question. If a magnetar is capable of this once, could it happen again? And could it happen on an even grander scale? No one was actively searching for magnetars at the time. The very term had not yet been coined. Scientists in the 1970 seconds were still developing their understanding of neutron stars and pulsars. These were the rapidly rotating remnants of stars, known for emitting regular radio pulses. Then, on March 5, 1979, the cosmos introduced humanity to something far more extreme. The gamma ray burst that struck Earth on that day did not conform to any existing scientific models. It was simply too bright, it was too brief, and it was far too energetic. The burst originated from a fixed point in the sky, not from some faraway galaxy. In the months that followed, that same spot continued to pulse with X-rays every 8 seconds. This was not the behavior of a typical pulsar. This was something new. Scientists began calling the object a soft gamma repeater, or SGR. The name was a description of what they were observing, not an explanation of what it was. It was a repeater, unlike most gamma ray bursts. Its energy spectrum was also softer, meaning it had lower energy than the gamma ray bursts seen from cosmological distances. But what could be the underlying cause of such behavior? An answer was proposed in 1992 by Robert Duncan and Christopher Thompson. Their calculations showed that a neutron star with a sufficiently powerful magnetic field could store vast reserves of energy within its twisted field lines. They theorized that when these lines snap and reconfigure, they would release powerful bursts of gamma rays and X-rays. They gave these hypothetical objects a name: magnetars, a portmanteau of magnetic and star. The theory was met with skepticism at first. Some scientists doubted that magnetic fields could ever attain such extreme intensities. Others raised questions about whether such a field could remain stable over time. But the observational evidence continued to accumulate. More SGRs were discovered over the years. Their observed behaviors aligned with the predictions of the magnetar model. Then, in 1998, researchers were finally able to measure a magnetar's magnetic field strength directly. They achieved this by observing what are known as cyclotron resonance features in the object's X-ray spectrum. When charged particles spiral within a magnetic field, they emit radiation at very specific frequencies. These frequencies are determined by the strength of the field itself. By measuring these frequencies in the X-ray light from a magnetar, scientists calculated field strengths of 10 to the 14th to 10 to the 15th Gauss. This was precisely the range that Duncan and Thompson had predicted. Since that confirmation, we have identified around 30 confirmed magnetars within our own galaxy and in nearby galaxies. It is likely that many more exist, which we have not yet found. They may be dormant, or they could be obscured from view by interstellar dust. Each one that we are able to study presents us with new puzzles. Some are remarkably active, erupting multiple times in a single year. Others can remain quiet for decades at a time. Some have been observed to emit radio waves, while others do not. We are still in the process of learning the rules that govern them. The discovery, however, has taught us something profound. The universe is capable of creating objects that are more extreme than we had ever imagined. And if magnetars exist, pushing magnetic forces to their theoretical limits, one has to wonder what else might be out there, pushing other fundamental forces to their own breaking points. On the 27th of August 1998, the Rossi X-ray Timing Explorer satellite was conducting routine observations of the sky. Suddenly, something extraordinary occurred. A magnetar with the designation SGR 1900+14 erupted in a massive flare. The resulting burst was so intense that it completely saturated the satellite's detectors. It overwhelmed them with a flood of X-rays far beyond what they were designed to handle. For a period of several hours, the telescope was rendered effectively blind. Its instruments had to be reset and recalibrated. Engineers back on the ground were concerned about the possibility of permanent damage. This was not the result of a design flaw. The satellite had been built specifically to study X-ray sources, but no one had anticipated an object that could suddenly grow 100,000 times brighter in less than a second. This incident was not an isolated one. Over the years, multiple X-ray satellites have been temporarily incapacitated by magnetar flares. In 2004, when SGR 180620 produced its own giant flare, it had an impact on over a dozen different spacecraft. Satellites like Swift, Integral, and RESI all registered the burst. Some of their instruments automatically entered protective modes to shield themselves. Others had their data corrupted by the sheer intensity of the incoming radiation. It is worth reflecting on what this truly means. These advanced satellites are in orbit around Earth. They are about 93 million miles away from our own star. They are engineered to observe X-ray sources that are billions of light-years away. Spacecraft are equipped with filters, shielding, and extensive safety protocols designed to manage intense radiation. Still, a magnetar located tens of thousands of light-years away possesses the power to overwhelm these defenses completely. The implications of this are profound. If a flare from a magnetar can effectively blind a satellite across such vast interstellar distances, one must consider what it could do at close range. The sobering answer is that nothing could withstand it. Any vessel within several light-years of a major magnetar eruption would be instantly incapacitated. The intense radiation would induce powerful currents throughout every circuit, melting the electronics from within. Solar panels would be rendered useless, degraded by the sheer force of the bombardment. Against such an onslaught, even the most robust shielding would prove utterly ineffective. What makes this particularly unsettling is the complete absence of any warning system. Magnetars provide no indication that they are about to erupt. There is no detectable precursor or signal that an event is imminent. In one moment, they can be relatively tranquil, emitting a steady stream of X-rays. In the next, they can detonate with an energy output rivaling thousands of supernovas, all compressed into a fraction of a second. This represents a hidden and unpredictable danger for the future of space exploration. As we venture with probes deeper into our galaxy, they could drift into the vicinity of magnetars we have not yet discovered. A probe might be journeying through the interstellar medium, entirely oblivious to a dormant magnetar just a few light-years away. Then, without any forewarning, that magnetar could awaken. The probe would cease to function before its own sensors could even register the event that destroyed it. In response to this threat, scientists are actively developing superior detection methods. Their goal is to create a comprehensive map of every magnetar in our galaxy and to monitor them continuously. An early warning could be the key to saving future missions. There is, however, a significant challenge. Dormant magnetars are nearly invisible to us. They radiate so little energy that our instruments can barely perceive their presence. This suggests there could be dozens, or perhaps hundreds, of them concealed within our galaxy, completely unknown to us. Each one of these is effectively a loaded weapon, simply waiting for the moment to fire. Our galaxy is home to an estimated 200 billion stars. Of those, approximately 1 billion are expected to end their lives as supernovas. A great number of these explosions will leave behind neutron stars. Scientists calculate there could be as many as 100 million neutron stars scattered across the Milky Way. Despite this vast number, we have only managed to confirm the existence of about 30 magnetars. The question then becomes, what makes these objects so exceptionally rare? The explanation begins with the circumstances of their birth. Not just any neutron star can evolve into a magnetar. The progenitor star must meet a specific set of conditions. It needs to be massive enough to form a neutron star, yet not so massive that its collapse results in a black hole. This is a very specific window, roughly between 8 and 20 times the mass of our own star. Mass alone, however, is not the only requirement. The star must also be spinning at an incredible speed at the moment of its collapse. As its core is crushed down into a tiny volume, the principle of conservation of angular momentum causes its rotation to accelerate dramatically. This rapid spinning, combined with convective churning within the collapsing matter, generates a powerful dynamo effect. It is this dynamo that amplifies the star's magnetic field to such extraordinary levels. One can imagine it as a kind of cosmic generator. The collapse itself provides the raw initial energy. The spinning motion then organizes that energy, shaping it into a coherent and immensely powerful magnetic field. But this process is successful only when the conditions are perfectly aligned. The rotational speed, the distribution of mass, and the initial magnetic field strength must all fall within precise parameters. Such a confluence of factors is exceedingly rare. Even after a magnetar is formed, it does not remain in that state indefinitely. Its extreme magnetic field begins to decay gradually over an extended period. Scientists estimate that magnetars stay in their active phase for only about 10,000 years, and possibly even less. Following this period, the field weakens until it reaches the level of a typical neutron star. The object then settles into a more stable existence, becoming an ordinary pulsar or just a quiet, cooling neutron star. This remarkably short active lifespan helps to explain why we observe so few of them. At any given time, Only a very small fraction of all neutron stars are passing through their magnetar phase. The others have either not yet entered this stage or have long since moved past it. It represents a brief and violent chapter in the long life of a neutron star. Yet there is another factor contributing to our low count: the difficulty of detection. Magnetars are incredibly small, measuring only about 12 miles in diameter. They are also incredibly far away, often tens of thousands of light years from Earth. And unless they are in the midst of an active flare, they are exceptionally dim. A great many may be in a dormant state right now, invisible to our telescopes, awaiting their next violent outburst. We typically only discover magnetars when they do something spectacular. A major flare causes them to light up across the entire electromagnetic spectrum. It is only then that we can study them, measure their unique properties, and confirm their identity as magnetars. But a quiet one could be lurking much closer, and we would have no way of knowing it was there. In fact, many scientists suspect that the true number of magnetars is far greater than what we have confirmed. There could be hundreds in our galaxy alone. The majority are likely dormant, their surfaces slowly cooling as their magnetic fields gradually weaken. They will inevitably flare up again, perhaps in years, decades, or even centuries. Until that happens, they remain hidden from our view, which means one could be nearer than we currently imagine. In space, distance is usually a reliable form of safety. A supernova exploding 10,000 light-years away is a magnificent spectacle, but poses no danger. Even a gamma-ray burst, if not aimed directly at us, is harmless from such a distance. Magnetars, however, completely alter this calculation. Scientists have modeled the potential outcomes, and the results are deeply disturbing. If a magnetar within 10 light-years of Earth were to unleash a giant flare, an event comparable to the one in December 2004, the resulting radiation would be devastating. The burst would strike our atmosphere with enough energy to partially destroy the ozone layer. Without this protection, ultraviolet radiation from our own star would surge. Widespread extinction events would likely follow. A more sobering thought for astronomers, however, is the proximity. 10 light-years is exceptionally close in cosmic terms. There are only about a dozen stars within that radius of Earth. The probability of a magnetar being among them is extremely low. But at a distance of 10,000 light-years, there are millions of stars, and we know for a fact that magnetars exist within that range because we have detected them there. A hyperflare from 10,000 light-years away would not annihilate our ozone, but it would still produce noticeable effects. The ionosphere would visibly light up across the globe, satellites would sustain damage, and global radio communications could fail. And if the flare were powerful enough, reaching the theoretical maximum that magnetars can achieve, it might cause biological harm even from that immense distance. The absolute worst-case scenario involves a magnetar hyperflare aimed directly at our planet. It's important to remember that magnetars emit focused jets of radiation from their magnetic poles. As these objects rotate, the beams sweep through space, much like the beam from a lighthouse. If Earth were to find itself in the path of one of these beams during a giant flare, we would receive its full, concentrated intensity, not just the scattered radiation. From 10,000 light-years away, such a beam could deliver a dose of radiation comparable to being near a nuclear detonation. This would not affect the entire planet, only the hemisphere facing the magnetar at that moment. But that would be more than enough. The resulting electromagnetic pulse would cause power grids to fail on a massive scale. The consequences for our planet would be devastating, as electronic components would be overwhelmed and biological tissue would absorb perilous amounts of gamma rays and X-rays. Scientists project that a magnetar hyperflare, even from such a great distance, has the potential to elevate global cancer rates for several decades following the event. While it might not trigger an immediate mass extinction, the outcome would still be a catastrophe of immense scale. An unsettling aspect of this threat is that there is no method for preparation, no available warning system, and absolutely no defense. It's conceivable that Earth's geological history already holds traces of previous magnetar encounters. The causes behind some of the planet's mass extinctions remain frustratingly unclear. In their investigations, researchers have searched the fossil record for indications of heightened radiation exposure. Certain geological layers do reveal mutations and cellular damage that align with the effects of radiation. Yet the origin of that exposure is still a mystery. Is it possible that a magnetar directed its energy toward Earth millions of years in the past? Although we cannot yet prove this hypothesis, the possibility is a chilling one, because at this very moment, a magnetar somewhere in the cosmos could be accumulating stress within its crust. In the coming years or decades, that crust is destined to fracture. Its magnetic field will then project a concentrated torrent of lethal energy across the galaxy, and our only recourse is to hope that our world is not in its trajectory. Try to envision standing upon the surface of a magnetar. The exercise is impossible, of course, because survival would be instantaneous. But if one could imagine it, the landscape underfoot would defy all our conceptions of solid matter. The crust is composed of pure iron, which has been compressed to densities millions of times beyond that of steel. This iron is arranged in a crystalline lattice of such perfection that it makes a diamond appear chaotic by comparison. It is, quite simply, the hardest material known to exist in the universe. Nothing we can engineer even begins to approach it. Laboratories on Earth have attempted to simulate these conditions, but they have consistently failed. The required pressures and densities are fundamentally beyond our technological capacity. This iron, however, is not a static substance. The profound magnetic field permeates it, inducing currents and swirling eddies of electric charge. These electrical currents, in turn, generate incredible heat. This is not the familiar warmth of a fire. We are speaking of temperatures reaching millions of degrees. The surface of a young magnetar can achieve a temperature of 10 million degrees, a figure that surpasses the heat of our own sun's core. At such extreme temperatures, even this crystalline iron begins to exhibit peculiar properties. The outermost layers, a mere few yards deep, exist in a state that is neither truly solid nor liquid. The atoms vibrate with such ferocity that they can slide past one another, behaving like a metal on the verge of melting, yet they are held fast by the object's crushing gravity. Farther down, the escalating pressure ensures the material remains solid, but the surface retains this strange plasticity. When a starquake occurs, this iron crust fractures, but not in the way that glass shatters. The crack propagates through the ultra-dense material at a substantial fraction of the speed of light. Moving faster than sound travels through any normal matter. The two sides of this fracture abruptly shift, a shearing motion that liberates the immense stored magnetic energy. The surface itself then ripples, with waves traveling through the solid iron much like ripples spreading across a pond. The difference is that these waves are moving through a medium that is billions of times denser than water. The entire magnetar resonates, vibrating at specific frequencies determined by its size, its mass, and its internal composition. These powerful oscillations can persist for weeks or even months, slowly diminishing as the energy is dissipated. Yet the surface does more than just crack and vibrate. It also erupts. The release of magnetic energy heats the surface material to billions of degrees in a span of microseconds. Despite the immense gravity attempting to hold it down, the iron vaporizes. A plume of ionized iron plasma, an atmosphere born of sudden violence, rises from the surface. This atmosphere is a transient feature, lasting perhaps only seconds or minutes before gravity inevitably pulls it back down. For those brief moments, however, the magnetar possesses a genuine, albeit thin, atmosphere that can be detected. Spectroscopic observations have in fact captured this phenomenon. When magnetars flare, their spectra reveal absorption lines corresponding to iron, silicon, and other elements. These spectral lines inform us about the surface's composition and its temperature. The data from these observations serves to confirm our theoretical models. The surface is indeed made of iron, and it is indeed unimaginably hot. Beneath this crust lies a substance that is stranger still, a liquid layer composed of neutrons that are no longer bound to protons, flowing without restraint. Scientists refer to this as a neutron superfluid, as it moves with absolutely no friction or viscosity. Deeper yet, these neutrons might condense into exotic states of matter that current physics can scarcely begin to describe. But all of this is concealed beneath the iron crust, and that iron itself is already a material beyond our full comprehension. The majority of magnetars do not possess atmospheres, at least not in the way we understand Earth's. Their gravity is so powerful that any gas would be pulled downward and compressed into the surface almost instantly. Magnetars do, however, have something else, a layer so thin it is barely present, yet so massive that it defies belief. Researchers call this a photosphere, though the term is not entirely precise. It represents the region from which photons can finally break free of the dense material below. In ordinary stars, the photosphere is thousands of miles thick. On a magnetar, its thickness is measured in centimeters, sometimes even less, forming a layer that can be just 1 atom deep. Yet that single layer weighs millions of tons per square inch. The density is so great that a single centimeter of this material contains more mass than an entire mountain. The photons that struggle to escape through this layer are scattered billions of times, ricocheting between atoms and electrons before they can finally emerge. This scattering process alters the spectrum of light that we observe, creating the unique fingerprints that allow us to identify magnetars. The magnetic field also plays a vital role here. Its strength is so overwhelming that it confines any material attempting to escape. Electrons, ions, and all other particles become trapped, forced to move along magnetic field lines but unable to cross them. The result is a highly structured environment, more akin to columns and sheets of plasma than a uniform layer of gas. When a magnetar flares, the magnetic field lines situated above the surface reconnect. This process of magnetic reconnection leads to a sudden release of the material that was trapped. Plasma that had been contained within magnetic loops is violently thrown outward at high speeds. For a short period, the magnetar develops a true atmosphere, which can extend for perhaps 100 miles above its surface. This ejected material then cools as it expands, emitting the X-rays and gamma rays that our telescopes can observe. The spectrum of this emission contains features that reveal the temperature, density, and magnetic field strength of the plasma. It provides one of the few direct ways we have to probe the conditions near a magnetar's surface. In the end, however, gravity always prevails. The liberated material does not possess enough velocity to escape the magnetar's pull entirely. It follows an arc back down, ultimately crashing into the surface at speeds of thousands of miles per second. This impact generates additional X-rays and more heat, and it can sometimes trigger subsequent magnetic activity. The entire sequence of events can last for many hours or even days. In the quiet intervals that fall between its violent flares, a magnetar's atmosphere all but vanishes from existence. Individual atoms may hover for a fleeting moment above the surface before gravity inevitably reclaims them. While charged particles can become ensnared by the magnetic field lines and spiral in a ceaseless dance, there is no continuous gaseous layer to speak of. There is no weather, nor is there any kind of atmospheric circulation, leaving only overwhelming gravity, blistering radiation, and magnetic field lines so intensely warped they construct cages of pure force. This environment is the closest approximation to a completely exposed stellar core that the laws of nature will permit. The surface of a magnetar represents matter pushed to its ultimate threshold, and physics stretched to its absolute breaking point. And yet, through some unknown mechanism, it remains fundamentally stable. It endures, A 12-mile sphere of apparent impossibility hangs in the cosmic darkness, serving as a profound reminder that the universe still harbors secrets we cannot yet explain. Albert Einstein's work established that gravity warps the fabric of space-time. The more intense the gravitational field, the more significantly time appears to slow down relative to a distant observer. We have confirmed this effect with exceptionally precise atomic clocks aboard airplanes and satellites. The phenomenon is undeniably real, but near a magnetar, time does not merely slow, it decelerates to a near standstill. When one calculates the gravitational time dilation at a magnetar's surface, the resulting numbers seem to defy logic. For every single second that passes for the magnetar, roughly 1.3 seconds elapse for an observer positioned far away in space. That represents a 30% discrepancy in the perceived flow of time. If you could somehow stand upon a magnetar for 1 year of your own time, approximately 16 months would have passed for the rest of the universe. This outcome is not speculative in nature. The mathematics involved are a direct application of straightforward general relativity. We are able to measure this phenomenon indirectly by carefully studying the light that emanates from magnetars. Photons that climb out of the star's profound gravitational field must expend a great deal of energy. They consequently become redshifted, their wavelengths stretched to longer, redder parts of the spectrum. The specific amount of this redshift tells us with great precision how powerful the gravity is. And these calculations have been found to match theoretical predictions with perfect accuracy. But this powerful time dilation gives rise to very strange situations. Imagine observing a magnetar from a great distance through a flawless telescope. You can clearly see its tormented surface. A powerful starquake suddenly occurs. From your remote perspective, the fracture spreads across the crust far more slowly than it would if you were standing right there. The oscillations that ripple through the star in the aftermath appear visibly stretched out in time. The entire momentous event gives the impression that it is happening in extreme slow motion. Meanwhile, if you were somehow located on the surface, time would feel completely normal to you. The crack in the crust would propagate at its true physical speed. The subsequent vibrations would ring out at their natural, unaltered frequency. You would not perceive anything unusual about the passage of time itself. It is only when you compare the reading of your clock to a distant observer's clock that the profound difference materializes. This has very real consequences for the physical processes that are happening on the magnetar. Nuclear reactions, the decay of particles, and all other processes that are dependent on time unfold at different rates depending on where you measure them from. A neutron near the surface, for example, would decay more slowly from an outside perspective than a neutron located far from the magnetar. This difference is a measurable quantity. Scientists use these time dilation effects to test the theory of general relativity under the most extreme conditions. Magnetars offer a unique natural laboratory where gravity is strong enough to create noticeable effects, but not quite strong enough to cause a total collapse into a black hole. They exist right on this critical edge, making them the perfect testing ground for our theories. Some researchers have even proposed that magnetars could be employed for precision tests of alternative gravity theories. If general relativity is going to break down anywhere, it would likely be here, where space-time is stretched to its very limit. So far, all our observations have perfectly matched Einstein's predictions. But we continue to watch, and we continue to measure, always hoping to find a small crack in the foundational theory. Because if general relativity does fail near magnetars, it would completely revolutionize the world of physics. We would require entirely new theories to explain what holds these objects together, how they behave, and why they do not collapse under their own weight. The implications of such a discovery would ripple outward through every single branch of science. But for now, Einstein's framework still reigns. Time bends near magnetars in exactly the way that he predicted it would. And that bending of time is yet another way these bizarre objects warp reality itself. There is a specific problem that keeps physicists awake at night. magnetic fields are known to decay over time. This is a constant. Every magnet you have ever held in your hand will eventually lose its magnetism. The atoms that are responsible for creating the field will slowly drift out of their precise alignment. Energy inevitably dissipates from the system as heat. This process is simply inevitable. So why do the magnetic fields of magnetars not decay? In truth, they do decay, but they do so on an incredibly slow timescale. Scientists estimate that a magnetar's field has a half-life of about 10,000 years. This means that after 10,000 years, the field's strength will have dropped by half. After another 10 millennia, it will halve in strength once again. Given a long enough span of time, a magnetar should eventually become an ordinary neutron star with a much weaker magnetic field. But here is the central mystery. The amount of energy stored within a magnetar's magnetic field is truly enormous. We are talking about a value of 1047 joules, which is roughly the mass energy equivalent of a small planet, according to Einstein's famous equation. That incredible amount of energy has to originate from somewhere, and it must be maintained somehow, at least for a very long time. The leading theory involves the magnetar's extremely rapid rotation. When a magnetar is first formed, it is thought to be spinning incredibly fast, possibly up to 1,000 times per second. This rotation, when combined with convective motions inside the newly formed neutron star, could generate the initial magnetic field through a powerful dynamo process. It is a mechanism similar to how Earth generates its own magnetic field, but it is cranked up to almost impossible extremes. But there is a significant catch to this idea. For this process to work, the magnetar requires a persistent power source to continue driving the dynamo. Its rotation provides some of that energy, but it is not enough on its own. Scientists now think the key might be found in the magnetar's complex internal structure. Neutron stars are not uniform spheres of matter. They have distinct layers, including solid crusts and superfluid cores. Different layers inside the star might rotate at slightly different speeds, creating tremendous shear forces between them. These powerful forces could be what maintains the unimaginably strong magnetic field. Another compelling possibility involves the presence of exotic matter. In the core of a neutron star, the pressures are so extreme that neutrons might actually break down into their constituent quarks. These quarks could then form strange states of matter, such as a quark-gluon plasma, or perhaps even stranger configurations. Some theories suggest that these exotic states possess unique magnetic properties that could sustain these ultra-strong fields. We do not yet know which of these theories is the correct one. It is possible that all of them contribute to the phenomenon. It is also possible there is another mechanism that we have not yet considered. The data we currently have is not detailed enough to rule out these competing options. We need more observations, better theoretical models, and perhaps even new physics to fully understand how magnetars maintain their fields. But here is what we do know for certain. The field is there. Its existence has been measured, its power has been confirmed, and it is doing things that should not be possible according to our standard models of magnetic field decay. Magnetars are violating our expectations at a fundamental level. They are pushing far beyond what we thought nature would allow. And every single new observation only raises a host of new questions. A curious observation has emerged that challenges our understanding, as some magnetars appear to possess magnetic fields that are growing stronger rather than decaying. This presents a deep puzzle for physicists. Furthermore, others display intricate field geometries that defy simplistic theoretical models. The magnetic environment of a magnetar is not merely powerful, it is a complex tapestry, twisted and knotted in configurations that we are only now beginning to chart. These extreme objects serve as a profound reminder that our grasp of magnetic fields, particularly under such immense energies and conditions, is far from complete. Until this fundamental mystery is unraveled, magnetars will likely remain just beyond the reach of our current theories. The behavior of these celestial objects is also strikingly inconsistent. Some are exceptionally active, producing dozens of eruptions each year. In contrast, others can remain quiet for decades, only to awaken abruptly with a colossal flare. This variability has been a central enigma for scientists since their discovery. The question of what governs a magnetar's temperament remains open. For instance, Skure 18006-20 was in a state of dormancy for more than 2 decades, a quiet and unremarkable object in the sky. Then, on the 27th of December 2004, it unleashed the most powerful burst ever documented, an event that sent a wave of astonishment through the entire astronomical community. The precise trigger and the timing of this eruption are still subjects of intense investigation. This stands in stark contrast to SG 1900+14, which is recognized as one of the most volatile magnetars ever observed. It experienced hundreds of eruptions between 1998 and 2002, ranging from minor bursts to significant cosmic events. Afterward, its activity subsided, and it now remains relatively calm, emitting only sporadic bursts. The reasons for this dramatic shift are not fully understood. Scientists have put forward several hypotheses to explain these behaviors. One prominent idea centers on the magnetar's age. It is thought that younger, more recently formed magnetars might be more active as their solid crusts are still settling into a stable state. During this period, the magnetic field is continually reconfiguring itself, leading to frequent starquakes and flares. As the magnetar grows older, it is expected to stabilize, causing its activity to diminish. While this model aligns with some observations, it does not account for all of them. Another theory directs attention to the geometry of the magnetic field. A field that is highly contorted and complex could potentially store a greater amount of energy, resulting in more frequent magnetic reconnection events that release this energy. Conversely, simpler field structures might be inherently more stable. A significant challenge, however, is that we cannot directly view the structure of a magnetar's field. Our understanding must be inferred from the timing and spectral properties of its bursts, a method that leaves considerable room for uncertainty. The temperature of the magnetar could also be a critical factor. These objects cool down over vast timescales as they radiate their internal heat into space. A hotter magnetar may have a more fluid interior, permitting more dynamic interactions between its crust and core. This could, in turn, trigger a higher frequency of starquakes. As it cools, the interior is thought to become more rigid, leading to a decrease in activity. This idea finds some backing in observations of their thermal emissions. Yet, no single theory provides a complete explanation for all the available data. Certain magnetars defy the expected patterns, remaining active for longer than predicted or falling silent much earlier. The sudden reawakening of dormant objects, exemplified by the 2004 event, suggests that even a seemingly quiescent magnetar can conceal immense internal stresses ready to be unleashed. It's also possible that external influences, which have not yet been fully considered, are at play. Interactions with other nearby celestial bodies could potentially trigger these flares. If a magnetar exists within a binary star system, the gravitational pull of its companion might create tidal stresses that build up and eventually cause the crust to fracture. While most known magnetars seem to be isolated, it is conceivable that we have overlooked faint companions in some cases, or perhaps the process is inherently random. Stresses may accumulate in a chaotic fashion, and the exact moment the crust finally gives way could depend on a multitude of small factors that are impossible for us to measure or predict. In this sense, magnetar flares might be fundamentally unpredictable, much like earthquakes on our own planet, existing only within the realm of statistical probabilities. This unpredictability is both a source of fascination and frustration for researchers. It implies that every magnetar must be treated as a unique case study. It also means we have no way to forecast when the next great flare will occur. The only course of action is to continue our observations, wait patiently, and hope our instruments are aimed correctly when it happens. Gamma-ray bursts represent the most luminous events known to exist in the cosmos. For a brief period, a single gamma-ray burst can outshine the combined light of every other object in the entire observable universe. Astronomers have registered these powerful flashes from galaxies billions of light-years away, so far that their light has journeyed for a significant portion of the universe's history, and it now seems that magnetars could be responsible for creating some of them. The majority of gamma-ray bursts are understood to originate from two specific sources. Long-duration bursts, which last for more than 2 seconds, are produced when massive stars collapse into black holes. Short-duration bursts, lasting less than 2 seconds, are the result of neutron-star collisions. There is, however, a third category of bursts that does not neatly fit into either of these classifications. They are too brief to be from collapsing stars, yet too brilliant to be from typical neutron-star mergers. Moreover, their energy spectra contain features that are consistent with those seen in magnetar flares. When SKIR 18006-20 unleashed its giant flare in 2004, the event was so powerful it would have been briefly visible from the Andromeda galaxy, located 2.5 million light-years from Earth. If an identical event were to take place in a very distant galaxy, perhaps 10 billion light-years away, we would detect it as a short gamma-ray burst. It might have been classified as a neutron-star merger or another type of cosmic event, with its true magnetar origin remaining hidden. This insight has fundamentally altered our interpretation of gamma-ray bursts. It suggests that some bursts previously attributed to other phenomena might actually be giant flares from magnetars. If this proves to be correct, it would imply that magnetars are significantly more prevalent than we currently believe. Every galaxy could be home to dozens or even hundreds of these objects, each one capable of producing bursts detectable across vast cosmic distances. Yet, there is an even more compelling connection to consider. Some scientists propose that magnetars could be the power source behind certain kinds of supernovae. This doesn't refer to the supernova that gives birth to the magnetar, but rather to subsequent cosmic events. The mechanism could work as follows. A young, rapidly spinning magnetar could inject a tremendous amount of energy into the expanding cloud of debris from its parent supernova. This additional energy would cause the supernova to appear exceptionally bright and to last much longer than a standard one. We have indeed observed supernovae that do not conform to conventional models. They are either too luminous or their light fades too slowly. Researchers have termed these events superluminous supernovae. The spectra of some of these are consistent with emissions powered by a magnetar. The energy from the magnetar's slowing rotation, a process known as magnetic braking, is converted into radiation that illuminates the surrounding gas. It is akin to having a cosmic light bulb glowing from within the supernova remnant. If this hypothesis is accurate, magnetars are not just objects of intrinsic interest. They are pivotal actors in a range of cosmic phenomena. They influence the evolution of supernovae and generate gamma-ray bursts. Through their violent eruptions, they may even distribute heavy elements throughout the universe. The material they eject into space, rich in iron and other metals, could contribute to the chemical composition of future generations of stars and planets. This intricate web of connections underscores just how vital magnetars are to the broader cosmic ecology. These phenomena are not isolated cosmic oddities. They are an integral part of the magnificent cycle of stellar birth, existence, and demise. With each one we study, our understanding of how the universe operates grows a little deeper. Consider a hypothetical scenario. A truly massive star, located approximately 200 light-years from our own solar system, reaches the conclusion of its life. It erupts in a supernova, creating a spectacular light show. From our vantage point, this display would be beautiful and completely harmless. The star's core, however, collapses under its own gravity, becoming a magnetar. What might follow? For a time, nothing at all. A distance of 200 light-years is vast enough that even a magnetar would present no immediate danger. Its magnetic field, while extraordinarily powerful up close, diminishes rapidly over distance, becoming negligible at our location. Beyond the supernova itself, we would detect nothing out of the ordinary. But magnetars are not known for remaining dormant. Within a few years or perhaps decades, this new object would likely experience its first major flare. If we imagine it producing an outburst similar in scale to the event of December 2004, the resulting radiation would speed toward Earth at the velocity of light, arriving 200 years after it was unleashed. This burst would briefly illuminate our night sky, not with the brightness of a full moon, but it would be distinctly noticeable, a new point of light, suddenly brighter than any star, that would appear and then vanish in less than a second. Astronomers would race to understand what they had just observed. Telescopes would pivot to its location, finding the magnetar, still pulsing and emitting X-rays. The concerning aspect emerges when we consider the dose of radiation. From 200 light-years away, the amount reaching Earth would be minor. We would see a slight spike in background levels, and some satellites might suffer from minor electronic glitches, but it would be far from a catastrophic event. Now, let's reimagine this scenario with the magnetar positioned only 20 light-years away. At this proximity, a giant flare becomes genuinely dangerous. The intense X-ray and gamma-ray radiation would penetrate deep into our atmosphere, inflicting significant damage on the ozone layer. While not a complete obliteration, the harm would be enough to elevate surface UV radiation for years, leading to a rise in cancer rates. Ecosystems that are particularly sensitive to UV light would face a struggle for survival. Marine plankton, which serve as the foundation of the ocean's food web, would experience a massive die-off. If we shrink that distance to just 10 light-years, we enter the realm of catastrophe. A giant flare from a magnetar this close would constitute an extinction-level event. The ozone layer would be effectively shredded. Unfiltered ultraviolet radiation from our own sun would sterilize the planet's surface. Complex life would be forced to retreat into deep caves or the abyssal zones of the oceans. Some species might endure, but the majority would not. Human civilization would face an inevitable collapse. What is truly unsettling is the fact that we would have no knowledge of the event until it was already happening. The flare's radiation travels at light speed, so there is no advance warning. One moment, the world is normal. The next, our sky is lit by a deadly wave of energy. By the time we could detect it, we would already be immersed in it, with no time to prepare and no way to protect ourselves. Fortunately, the likelihood of this is exceedingly low. The massive stars that can produce magnetars are rare, and most are very far away. The closest known candidate is probably more than 100 light-years from us. Even if it were to go supernova, the probability of its core forming a magnetar instead of a black hole or a standard neutron star is perhaps only 1 in 10. The subsequent chance of it directing a flare toward Earth during its relatively brief active life is smaller still. Yet, the universe is ancient and immense. It is conceivable that somewhere, at some point in time, a civilization might not be so fortunate. They could find themselves living near a magnetar, and when it awakens, their story would abruptly end. Black holes tend to capture all the attention. They are portrayed as the universe's ultimate agents of destruction, objects that consume everything in their path. Not even light can escape their grasp. Popular culture has embraced them, often casting them as cosmic antagonists in films. But if you were to ask a physicist which of these objects is actually more dangerous, you might receive an unexpected answer: magnetars. The argument rests on their method of destruction. Black holes destroy through gravity. If you venture too close and cross the event horizon, you are irrevocably lost. But the event horizon itself is quite small. For a stellar mass black hole, it might be only 60 miles across. As long as you remain outside that radius, you are relatively safe. There is, of course, radiation from an accretion disk if the black hole is actively feeding, but a dormant black hole, one not consuming matter, is essentially invisible and harmless unless you happen to fly directly into it. Magnetars, by contrast, can inflict harm from a great distance. Their magnetic influence extends for thousands of miles, and their bursts of radiation can travel across light years. They do not need to be nearby to cause immense damage. A magnetar flaring 10 light-years away could be fatal, while a black hole at that same distance would be just another dark, silent object in space. The scale of their destructive range is fundamentally different. Scientists have calculated these danger zones. For a black hole, the lethal radius where gravity would tear you apart is measured in thousands of miles at most. For a magnetar, however, the lethal radius from a giant flare can extend out to potentially dozens of light-years, a volume that is billions of times larger. Advocates for the black hole's supremacy push back, arguing that black holes are eternal. A magnetar's active phase may last for only 10,000 years or so, but a black hole will exist until the very end of the universe. Given enough time, a black hole will consume far more matter, erase more cosmic structures, and have a greater cumulative effect. They also point to the supermassive black holes that reside at the centers of galaxies. These behemoths contain the mass of billions of stars. When they actively feed, they launch jets of radiation and matter that can stretch for hundreds of thousands of light years, sterilizing entire galactic regions, halting star formation, and extinguishing any life that might have arisen. No magnetar can match that scale of destruction. Yet, supporters of the magnetar have a compelling counterargument. The destruction from a supermassive black hole is a gradual process that unfolds over millions of years. A magnetar flare is instantaneous, capable of ending a civilization in less than a second. There is something uniquely terrifying about that immediacy. Black holes afford you time, magnetars do not. There is also the matter of which is more violent relative to its size. A magnetar just 12 miles across can unleash more energy in a fraction of a second than thousands of stars produce over many years. Even an actively feeding stellar mass black hole cannot equal that raw power output. On a pound-for-pound basis, magnetars are the clear winners. The debate remains unsettled. Both objects represent physics taken to its most extreme limits, and both are capable of ending worlds, though they do so in different ways. Black holes erase through gravity, a slow and inevitable process. Magnetars attack with radiation and magnetism, a sudden and explosive assault. Perhaps the truest answer is that we should be wary of them both. The cosmos possesses a multitude of ways to extinguish life, and to argue which is more severe feels futile when any of them occurring near our planet would mean the end of civilization. With the exception of hydrogen, every atom that constitutes your body was born from the stars. This is not a poetic sentiment. It is a confirmed scientific reality. Elements like carbon, oxygen, nitrogen, and iron were all forged in the cores of stars and then scattered into the void when those stars perished. A profound mystery, however, lies in the existence of certain heavy elements. The truly massive ones appear in quantities that our current understanding struggles to explain. The creation of elements heavier than iron demands very particular circumstances, including intense bombardment by neutrons, temperatures reaching billions of degrees, and incredibly precise timing. While supernovas can supply some of these conditions, and collisions between neutron stars can provide even more, our calculations indicate that these sources alone are insufficient to account for all the heavy elements observed throughout the universe. Another cosmic contributor must be at play. This is where magnetars enter the picture. When a magnetar erupts in a flare, it does more than just release radiation. It also ejects matter from its surface. This material, rich in neutrons, is blasted into space at a substantial fraction of the speed of light. The ejector is unimaginably dense, filled with neutrons that have not yet had time to decay, and it travels through a field of radiation so intense it can drive nuclear reactions. These conditions are ideal for the rapid neutron capture process, known as the R process, which is responsible for creating heavy elements. In a matter of milliseconds, neutrons are slammed into existing atomic nuclei, building progressively heavier atoms. Gold, platinum, and uranium elements that are both rare and valuable on Earth are formed in great abundance during these extraordinarily violent episodes. The magnetar, in essence, acts as a cosmic foundry, manufacturing heavy elements through sheer force. Scientists have discovered compelling evidence for this process within samples from meteorites. Certain ancient meteorites contain isotopic ratios that do not align with the predictions for supernova events. Instead, they exhibit an excess of specific heavy elements, enriched beyond what standard models can produce. What's intriguing is that these ratios closely match what would be expected from R-process nucleosynthesis occurring within extreme magnetic fields. The implications of this are truly staggering. It is possible that every single atom of gold in existence journeyed through a magnetar flare billions of years ago. The platinum used in catalytic converters, the uranium that fuels nuclear reactors, and the rare earth elements essential for modern electronics may all have been created during moments of inconceivable violence on the surfaces of magnetars. The story, however, does not end there. The ejected material does not simply drift into the interstellar medium. It collides with the surrounding gas and dust at immense velocities, generating powerful shock waves. These shock waves compress the interstellar material, which in turn can trigger the formation of new stars. Any new stars born from the remnants of magnetar ejector would be enriched with heavy elements from their very inception. The planets forming around them would possess more metals and a more complex chemistry, potentially offering more favorable conditions for the emergence of life. This establishes a remarkable feedback loop. Magnetars forge heavy elements, and those elements then contribute to the formation of new stars and planets. Some of those stars will eventually evolve into magnetars themselves. The cycle persists, gradually enriching the universe with ever heavier elements. Over the course of billions of years, this mechanism fundamentally alters the chemical makeup of entire galaxies. We may, in fact, owe our very existence to magnetars. Earth's iron core, the metals that underpin our technology, and even the trace elements vital for biology could have their origins in magnetar flares that occurred long ago. Without these violent cosmic events, our world might have been too poor in metals to support the development of complex life. So, the next time you hold a piece of gold or use a device containing rare earth elements, it is worth remembering that this matter endured the most extreme conditions known in the universe. It was forged in magnetic fields that can warp the fabric of reality, ejected in flares that momentarily outshine entire galaxies, and then scattered across space to ultimately become a part of our world. The universe often creates through destruction, and magnetars stand as its most efficient and powerful creators. In the year 2007, astronomers made a detection that was completely unexpected. They observed a brief pulse of radio waves, lasting a mere 5 milliseconds, which had traveled from billions of light-years away. This burst packed as much energy as our sun releases in an entire day, all compressed into a time span shorter than a single heartbeat. They named this phenomenon a fast radio burst, or FRB, and its cause was a complete enigma. Initially, many scientists suspected it was some kind of error, perhaps radio interference from a terrestrial source or a satellite glitch, anything other than a genuine signal from deep space. But then more of these bursts began to appear, detected by different telescopes in different parts of the world, all observing similar transient pulses. By 2020, astronomers had catalogued more than 1,000 fast radio bursts. It was clear they were real, relatively common, and profoundly mysterious. What made them so peculiar was a combination of factors. The bursts seemed to originate from random directions all across the sky. For the most part, they were one-off events that did not repeat. They exhibited no discernible pattern. The amount of energy required to generate them was immense, yet the source itself had to be incredibly small to be able to pulse so rapidly. Only a compact object, like a neutron star or a black hole, could flicker on a millisecond timescale. But what exactly were these objects doing? A critical clue emerged when some fast radio bursts were observed to repeat. The same point in the sky would emit another pulse days or months later. This was a crucial piece of information because it meant the source was not destroying itself in the process. Whatever was creating these bursts was able to survive and burst again. This discovery effectively ruled out catastrophic, one-time events, such as supernova explosions or the merger of two neutron stars. The major breakthrough arrived in 2020. A fast radio burst was detected from within our own Milky Way galaxy. Its location in the sky perfectly matched that of a known magnetar, SGR 1935 plus 2154. Furthermore, the timing of the burst corresponded with a period when that magnetar was known to be actively flaring. The connection was undeniable. It became clear that at least some fast radio bursts originate from magnetars, but the question remained, how? Magnetars are known to emit high-energy X-rays and gamma rays during their flares. Radio waves are entirely different, representing a much lower form of energy. Generating such an intense burst of radio emission requires very specific conditions. Charged particles must be accelerated within magnetic fields and then be made to emit their radiation coherently. This represents a complex physical process that researchers are still working to fully comprehend. The leading theory involves an event known as magnetic field line reconnection, occurring just outside the magnetar. When the magnetar's powerful field lines snap and violently reconfigure themselves, they generate enormous electric fields that accelerate electrons to nearly the speed of light. As these high-speed electrons move through the intense magnetic field, they emit what is known as synchrotron radiation. Under just the right circumstances, this radiation can become coherent, amplifying itself into a powerful, focused beam of radio waves that shoots out into space. It is important to note that not all scientists are in agreement with this explanation. Some have argued that magnetars alone cannot produce the very brightest fast radio bursts that have been detected from other galaxies. Those events, they suggest, would require even more extreme conditions. These researchers have proposed alternative models that involve binary star systems, strange quark matter, or perhaps even more exotic physics. The scientific debate on this fascinating topic continues. What we now understand is that fast radio bursts have evolved into an essential tool for investigating the wider universe. As these powerful radio waves travel across the vastness of intergalactic space, they are subtly dispersed by the free electrons they encounter along their journey. By carefully measuring the degree of this dispersion, astronomers can calculate the total amount of matter the signal has traversed. This measurement, in turn, reveals crucial information about the distribution of material between galaxies, the diffuse, cosmic web that is normally impossible to see. The study of fast radio bursts has also led to the realization that the universe is a more crowded place than we once imagined. If magnetars are indeed the engines producing these signals, and we are detecting thousands of them originating from distant galaxies, it implies that magnetars must be exceptionally common. It's possible that every galaxy hosts a population of hundreds, or even thousands, of these objects. The bursts we capture are merely the most visible signs of a truly immense population. An even more profound detail is that some of these fast radio bursts are arriving from sources that are billions of light years away. The signals themselves departed from their cosmic homes when the universe was still in its youth. In effect, we are detecting the echoes of magnetar violence from the era of cosmic dawn. And if magnetars existed so early in cosmic history, they may have played a role in shaping the early universe in ways we are only just beginning to contemplate. Within every magnetar resides a deep physical mystery. We know that the outer crust is composed of crystalline iron, and beneath that lies a layer of neutron superfluid. But it is the core, the very center where pressures reach their absolute zenith, that our understanding of physics becomes strange. Some physicists theorize that this core might contain a form of matter that exists nowhere else in the cosmos. At the heart of a magnetar, the pressure can reach 1 to 2 times 10 to the 35 pascals, a number so vast it becomes almost abstract in everyday terms, representing a force billions of times greater than the pressure at the core of the Earth. Under these extreme conditions, neutrons themselves may break down into their fundamental components, known as quarks. This process could create what is called quark matter, a state so incredibly dense that the boundaries separating individual particles begin to dissolve. Quarks are normally found in stable groups of 3, which form protons and neutrons. But under such immense pressure, these groupings might completely dissolve. The quarks would then be able to flow freely, creating a quark-gluon plasma that is thought to be similar to the state of the universe just microseconds after the Big Bang. While laboratory experiments in particle colliders have managed to create minuscule quantities of this material for fleeting moments, inside a magnetar, it could potentially be a stable and permanent feature. Yet there is an even more exotic possibility: strange quark matter. Quarks are known to come in 6 different types, or flavors. The familiar up and down quarks are what constitute normal matter. But there are also strange quarks, charm quarks, and top and bottom quarks. Under normal circumstances, these other, more exotic quarks are highly unstable and decay almost instantly. However, at the pressures found in a magnetar's core, strange quarks might achieve stability. If this were to happen, the core could undergo a transformation into strange quark matter, a substance that has been theorized but has never been confirmed to exist. This material would be even denser than normal neutron matter and could be fundamentally more stable. In fact, some calculations suggest that strange quark matter may represent the true ground state of all matter, implying that the regular atoms we see around us are simply in a metastable configuration, waiting for the right conditions to convert. This line of thought leads to a truly unsettling scenario. If strange quark matter is indeed more stable, any contact it makes with normal matter could initiate a chain reaction. The normal matter would instantly convert into strange matter upon contact, a process that releases energy and triggers further conversions. In theory, a single, tiny speck of strange matter could convert an entire planet in a matter of minutes. Scientists refer to these hypothetical objects as strange stars or quark stars. From an external perspective, they would appear very similar to neutron stars, having a comparable size, mass, and surface gravity. Their interior, however, would be fundamentally different. Some researchers speculate that magnetars might actually be quark stars instead of neutron stars, and that their extraordinarily powerful magnetic fields could be a signature of the exotic matter contained within. The evidence supporting this idea is currently limited. Certain observations of magnetars reveal properties that do not perfectly align with pure neutron star models. Their measured masses, radii, and cooling rates sometimes show slight deviations from what is predicted. These discrepancies could be an indication of an exotic composition, but the data remains inconclusive. It is also possible that regular neutron stars with unusual internal structures could account for these observations. To truly test this hypothesis, we require better measurements. We need to determine the masses and radii of magnetars with much greater precision. We also need to observe their cooling behavior over many decades and detect any gravitational waves they might produce. These measurements could finally reveal whether their cores are made of neutrons or of something far stranger. The implications of this research extend well beyond magnetars. If quark matter is found to exist stably in nature, it would fundamentally alter our understanding of matter itself. It would mean that the periodic table is not the final chapter in the story of matter. Denser, more compact arrangements of quarks could be waiting to be discovered. And somewhere in the universe, within the cores of the densest objects known, that matter may exist right now. We might be living in a cosmos where most matter is in an excited state, prevented from reaching its true form only by the absence of extreme gravitational pressure. The cores of magnetars could be windows into the fundamental nature of reality, showing us what matter truly becomes when gravity strips away all pretense. On February 18, 2008, the European Space Agency's integral satellite was engaged in a routine gamma-ray survey. Its instruments were perfectly calibrated, and all its systems were operating as expected. Then, without any warning, every single detector on the satellite went blind. The data stream being sent back to Earth suddenly filled with incomprehensible noise. Engineers on the ground worked frantically to understand what had just occurred. The source of the disruption was identified as SGR 0508-66, a magnetar located approximately 16,000 light-years from Earth. It had erupted in a flare of immense power, unleashing a wave of gamma rays and X-rays that swept across the galaxy. The burst itself lasted for only a few seconds, but in that brief time, it exposed integral to more high-energy radiation than the satellite would normally receive over a period of months. Integral was not designed to withstand such an event. Its instruments were capable of handling typical gamma-ray sources, even very powerful ones. But a magnetar flare at what is, cosmically speaking, close range, completely overwhelmed every one of its safety margins. The detectors became saturated. The satellite's electronics were subjected to massive induced currents from the powerful electromagnetic pulse. For several minutes, the sophisticated satellite was rendered effectively useless. But what is truly remarkable is that Integral survived. Its onboard systems initiated an automatic reboot. The detectors reset themselves. Within an hour, the satellite was back online, slightly damaged but fully functional. It had been struck by a wave of radiation with an energy equivalent to a point-blank nuclear explosion, and yet it continued to work. This outcome was the result of excellent engineering combined with an incredible stroke of luck. The good fortune was in the satellite's orientation. At the precise moment the burst arrived, Integral happened to be positioned in such a way that its main instruments were pointing away from the magnetar. The spacecraft's orientation proved fortunate, as the radiation struck its side instead of its delicate detector surfaces. A different alignment would have exposed the instruments to the full, direct impact of the outburst. It is highly improbable they would have survived such an event. Not every satellite in the flare's path was as lucky. The Swift satellite, a craft specifically engineered to observe gamma-ray bursts, was also watching the skies as the flare arrived. Its instruments were overwhelmed even more thoroughly than Integral's. The recovery process took hours to complete. A few of its detectors even sustained lasting damage, exhibiting a subtle degradation in performance for the remainder of their operational lives. Farther away, the Mars Odyssey orbiter, circling the planet Mars, also registered the burst. What's remarkable is that this spacecraft was never intended to observe gamma rays. The flare's intensity was so profound, however, that its radiation sensors, designed to track particle flux in the Martian environment, were driven completely off the scale. For a brief period, the orbiter's systems behaved as if it were enduring a massive solar storm. It was only later that scientists understood the radiation had traveled from the other side of our galaxy. This incident served as a stark lesson for spacecraft designers. It was a clear demonstration that the universe holds dangers beyond what had been fully anticipated. While magnetar flares are infrequent, their consequences can be catastrophic when they do happen. Future missions into deep space must incorporate shielding and protection against abrupt surges of radiation that could arrive from any direction with no advance notice. Consequently, NASA and other space agencies now integrate magnetar flares into their formal risk assessments. For any mission venturing to the outer solar system, especially those designed to operate for many decades, the likelihood of encountering at least one significant magnetar event becomes substantial. Engineers are now developing more resilient electronics, improved shielding materials, and automated safety systems capable of reacting within milliseconds. Yet, there are practical limits to what can be achieved. A truly colossal flare, one on the scale of the March 1979 event, would likely obliterate most spacecraft, regardless of their protective measures. The sheer intensity of the radiation would be overwhelming. Electronic systems would be instantly disabled. Solar panels would suffer immediate and catastrophic degradation. Even the physical structure of a spacecraft could be compromised by the powerful electromagnetic fields, which would induce destructive currents in its metallic parts. The risks become even greater for future interstellar probes. As we begin to send craft toward the nearest stars, they will traverse deep space for decades or even centuries. The probability that a magnetar flare will intersect their trajectory grows with the passage of time. It is conceivable that we could lose these distant explorers to phenomena we can neither foresee nor defend against. This is a sobering realization. Our aspirations to explore the galaxy are ultimately tempered by the galaxy's own inherent violence. Every magnetar is destined to fade. This is not a death in a fiery explosion, but rather a slow diminishment of its power. Its magnetic field will gradually weaken, its spin will decelerate, its surface will cool. In time, the object that once dominated its cosmic neighborhood with such ferocity will fall silent. But the question of what happens next has been a subject of scientific debate for decades. The answer, it seems, hinges on the magnetar's mass. Just as mass dictates the birth of such an object, it also determines its final destiny. The crucial boundary lies at approximately 2 to 3 times the mass of our own Sun. This is known as the Tolman-Oppenheimer-Volkoff limit. It represents the maximum mass that a neutron star can have before gravity overcomes the force of neutron degeneracy pressure. The majority of magnetars are thought to be below this critical limit. They were born from stars massive enough to produce neutron stars, but not so massive that their cores surpass this threshold. For these magnetars, the fate is not to become a black hole. Instead, they will simply fade away. Over millions of years, their magnetic fields will decay. Their rotation will slow to a single turn every few seconds or even minutes. The surface temperature will drop to nearly absolute zero. The resulting object is sometimes called a black dwarf, though this name can be confusing as it bears no relation to white dwarfs. It is simply a cold, inert neutron star. It remains a body of incredible density, still bending space-time around it, but it no longer emits any detectable radiation. It becomes a dark sphere, drifting through the void, imperceptible unless another object ventures close enough to be influenced by its gravity. Some magnetars, however, might exist right on this precarious edge. If a magnetar's mass is exceptionally close to the limit, its stability might depend on the outward pressure generated by its magnetic field and rapid rotation. As these sources of energy wane, the support they provide weakens. The magnetar could eventually slip past the critical threshold. In that single moment, gravity would triumph. The neutron star would collapse in on itself, forming a black hole. From an external perspective, this process would be remarkably quiet. There would be no grand explosion, no brilliant flash of light. The magnetar would simply cease to exist, its place taken by a tiny black hole, perhaps only 20 kilometers in diameter. Its magnetic field would vanish. Its rotation would become irrelevant. The object would have transitioned from one extreme state of matter to another. This transformation has never been witnessed. It may occur too swiftly for us to ever capture it. Alternatively, magnetars might shed enough mass through particle winds and radiation over their lifetimes to safely drop below the critical threshold, making collapse impossible. The truth remains unknown. Theoretical models yield different outcomes based on the assumptions made about the equation of state, which describes the relationship between pressure and density within ultra-dense matter. Another intriguing possibility is accretion-induced collapse. If a magnetar is part of a binary system, it could pull material from its companion star. This accumulation of additional mass could be enough to push it over the limit. In such a case, the neutron star would collapse into a black hole while still relatively young and active. This scenario could potentially account for some of the unexplained transient events that astronomers have observed. A number of researchers have suggested that we might be able to detect these collapses through gravitational waves. As a magnetar rapidly contracts into a black hole, it should release a short burst of gravitational radiation. Observatories like LIGO and Virgo could potentially register these signals if such an event were to happen within our cosmic vicinity. To date, no definitive signal has been found, but the field of gravitational wave astronomy is still in its infancy. Our universe may hold billions of these dead magnetars, scattered throughout the galaxies. They are the invisible relics of a violent past, too cold to radiate and too small to be seen unless one is practically upon them. And scattered among them could be small black holes, the final state for magnetars that crossed the ultimate mass threshold. From a distance, we would have no means of distinguishing one from the other. But no matter which final path a magnetar follows, its reign of terror is finite. It is a story of perhaps 10,000 years of extreme violence, followed by millions or billions of years of profound silence. The universe's most extreme objects are, in a way, also among its most ephemeral. They burn with an astonishing, brief brilliance, and then disappear into the darkness, their existence remembered only by the lingering scars they left on space-time itself. Physics has its limits. The boundaries of our understanding are not set merely by our incomplete theories, even though they are, but by the intrinsic limits of nature itself. There are ultimate thresholds for temperature, density, and field intensity, points beyond which the physical laws we rely on completely fail. Magnetars exist at the very edge of several of these fundamental constraints. Let us begin with the strength of magnetic fields. In principle, a magnetic field could grow infinitely strong, but in reality, this is not possible. At a level of around 10, the 17 Gauss, the field's energy density would become so great that it would surpass the mass energy density of matter. The field would then bend space-time more than the very object generating it. It would become gravitationally self-aware, in a sense, producing its own gravity. This threshold is known as the quantum critical field strength. Magnetars can produce fields reaching 10 to the 15 grams. This is just 1% of the quantum critical limit, yet it is close enough for quantum phenomena to become significant. In this environment, virtual particles within the vacuum begin to react to the field. Photons can split in two. The vacuum itself acquires a polarity. We find ourselves in a domain where the principles of quantum mechanics and general relativity begin to intersect. This is the very realm where our current theories find their greatest challenge. It is impossible to test physics under these circumstances in any terrestrial laboratory. The most powerful sustained magnetic fields we can create reach perhaps 50 Tesla, which is equivalent to about 500,000 grams. We are able to generate more intense fields in brief pulses, but these last for only microseconds before the equipment is catastrophically damaged. Achieving the field strengths found in magnetars would demand energy levels far beyond our reach. Nature, it seems, has provided the laboratory we ourselves cannot construct. Next, we can consider the question of density. The cores of neutron stars can attain densities of approximately 10 to the 18 kilograms per cubic meter. This value is around 5 times the density of an atomic nucleus, known as nuclear density. At such extreme compression, the neutrons are packed together so tightly that they are in direct contact. There is simply no remaining space between them, and we do not have a complete picture of what occurs when matter is compressed even further. Various theoretical frameworks offer differing scenarios. Some models suggest the matter simply remains as even more compressed neutrons. Other theories propose that quarks become deconfined, which would result in a state known as quark matter. Still, other ideas put forward the existence of exotic states of matter with names like color superconductivity or pion condensation. We possess the equations for these possibilities, but we lack the data to determine which set of equations is accurate. Magnetars and neutron stars in general serve as natural testing grounds for these very ideas. The gravitational time dilation near a magnetar also approaches a physical limit. On the surface of one of these objects, time passes 30% more slowly than it does in distant space. While this is not as extreme as the time dilation near the event horizon of a black hole, the effect is substantial. It is significant enough that relativistic effects can be measured with great precision. Any inconsistencies with the predictions of general relativity would become apparent in observations of magnetars. Temperature represents another such frontier. Immediately after they are formed, the surfaces of magnetars can briefly reach 1 billion degrees or more. This is a temperature hotter than the core of any star. In such heat, thermal photons possess energies that are comparable to the rest mass of electrons. This allows particle-antiparticle pairs to materialize spontaneously from thermal energy alone. The line between matter and radiation becomes indistinct. Rotation introduces yet another physical boundary. A young magnetar is capable of spinning hundreds of times each second. At such velocities, its equator travels at a considerable fraction of the speed of light. Matter on the surface is subjected to immense centrifugal forces that counteract gravity. If it were to spin much faster, the magnetar would be torn apart. What we are observing are objects at the absolute physical limit of rotational speed before disintegration. In magnetars, all of these limits converge. We see extreme magnetism, extreme density, extreme gravity, extreme temperature, and extreme rotation. With the possible exception of the unseeable interiors of black holes, nowhere else in the cosmos do so many extreme conditions manifest in a single location at the same time. Magnetars truly are nature's laboratories for extreme physics, and their existence tells us something profound. The universe is capable of reaching these limits and maintaining them, at least for a while. Our theories often predict collapse, instability, or a complete breakdown under these conditions. And yet, magnetars are real. They are stable, or at least stable enough to persist. This suggests that our understanding, while certainly not complete, is fundamentally on the correct path. We are moving in the right direction. However, the data contains subtle clues that new physics may be waiting to be discovered. There are small discrepancies and behaviors that do not perfectly align with our predictions. These hints could simply be measurement errors, or they could be the first signs of fissures in our current theories, pointing toward a deeper reality. Each new observation brings us a step closer to knowing the answer. Since 2016, a peculiar signal has been tracked by astronomers. It is a repeating fast radio burst, given the designation FRB 121 + 65-2, which emits radio pulses from a faraway galaxy at irregular times. In contrast to most fast radio bursts, which flash once and are never seen again, this source is persistent, sometimes pulsing dozens of times in an hour. It then falls silent for days before erupting once more. The pattern appears chaotic, yet it is not entirely random. A statistical analysis of the signals reveals an underlying structure. The bursts tend to group together during specific windows of time. They are absent during others. A cycle of roughly 16 days seems to be hidden within the data, although not every cycle yields a detectable burst. The object creating these signals is following a timetable that we do not fully grasp. In 2020, scientists pinpointed the source to a star-forming region inside a galaxy, 500 million light-years from Earth. The precise location showed that it was close to a massive star, or the remnant of one. The timing of the cycle was consistent with what one would expect from a binary system. The system would involve two objects orbiting one another, and the most likely candidate for generating such powerful radio bursts was a magnetar. A plausible explanation for how this works can be outlined. A magnetar is in orbit around a more conventional star, such as a blue giant or a supergiant. As they circle each other, tidal forces create stress within the magnetar's crust. When the two stars are at their closest point, which occurs approximately every 16 days, this stress reaches its peak. This event can trigger starquakes and magnetic flares. A portion of these flares generates radio emissions that are projected outward in a beam. When these beams are aimed at our planet, we detect them as fast radio bursts. However, not every orbit results in a burst that we can see. The radio emissions are focused into narrow beams, much like those from a lighthouse. A beam only reaches Earth if it happens to be oriented in our direction at the moment of the flare. Most of the flares produce beams that are pointed in other directions. We are simply unaware of them. This model helps to explain the irregular pattern of detection. The magnetar may be flaring on a predictable schedule, but we are only able to observe the events that are correctly aligned with our position. Other repeating sources exhibit different kinds of patterns. The source FRB 180 plus 57 displays a cycle of about 157 days. It will emit bursts for a period of several days, then become quiet for months, and then become active again. This much longer cycle points to a different kind of system, possibly a magnetar with a more distant companion star or a more elaborate orbital configuration. Some researchers, however, continue to be skeptical. Some researchers propose that the magnetar model may not be a universal explanation for all repeating bursts. There are instances where the energy released is simply too great, or the duration of the emissions is too brief to align comfortably with the theory. This suggests the possibility that multiple kinds of cosmic engines could be generating these repeating signals, with magnetars being just one of several potential sources. Other hypotheses point toward events like the merger of neutron stars that don't quite complete the process, or perhaps black holes that draw in matter through sporadic, intense episodes. Even more speculative ideas, such as those involving cosmic strings, have been put forward, though they are generally met with skepticism from the physics community. The discussion continues largely because the available data remains sparse. While we have now identified dozens of repeating sources, this number is still insufficient for drawing truly definitive conclusions. What is certain, however, in the study of repeating fast radio bursts is the unique window they open into the phenomena that create them. A solitary burst is a fleeting event, appearing and then disappearing forever. There is no chance for follow-up, no way to collect additional information. Repeaters, by contrast, allow us to aim an array of different telescopes at a known point in the sky and simply wait. When the source erupts again, we are prepared to capture it. This readiness allows for the measurement of polarization, the structure of frequencies, and variations in intensity, all with an extraordinary level of detail. These meticulous observations are uncovering a degree of complexity that was previously unsuspected. Some signals exhibit a drift in frequency, where the radio waves change their pitch during the pulse itself. Others are composed of multiple, smaller subpulses that arrive in tight clusters. The mechanisms responsible for these emissions must be incredibly sophisticated. likely involving elaborate magnetic field geometries and powerful particle acceleration. If magnetars are indeed the source, then these findings place significant constraints on how their magnetic fields must be arranged. The field cannot be a straightforward dipole, with a simple north and south pole. Instead, it must be a twisted and braided structure, featuring numerous active regions, each capable of generating its own distinct radio beam. This picture aligns well with theoretical models that predict how the magnetic fields of magnetars should evolve over time. And this is where the research becomes particularly compelling. New repeating sources are being discovered every month. As our telescopes grow more sensitive, we can detect ever fainter signals from more distant corners of the cosmos. Each new discovery adds another piece to the puzzle, allowing patterns to emerge from the data. With enough of these patterns, we will ultimately decipher the underlying principles. We will come to understand not only what is creating these powerful bursts, but also the reasons for their repetition, the forces that govern their cycles, and what this all reveals about the life of a magnetar. We have journeyed through a universe of extremes, from magnetic forces so strong they can bend the path of light, to densities so immense they warp the fabric of space-time itself. We have explored starquakes that can briefly outshine entire galaxies and radio signals that traverse the vast emptiness between them. We have seen how magnetars are born, how they live their violent lives, and how they might eventually fade away. Yet, beneath all this cosmic drama lies a fundamental truth, a realization that reframes our perspective on the universe. We are fragile, almost unimaginably so, and the cosmos operates with an indifference to our existence. A magnetar located 50,000 light-years from Earth has the capacity to inundate our world with radiation. A powerful flare, which we can neither predict nor prevent, could be unsurvivable if it were sufficiently strong. Our entire technological civilization, everything humanity has constructed, relies on a delicate balance of stable conditions, consistent radiation levels, a steady magnetic field, and a predictable climate. A single major magnetar flare pointed in our direction could cause that stability to vanish. What truly concerns many scientists, however, is that magnetars represent only one of many potential threats. The universe is filled with countless other dangers. There are black holes, gamma-ray bursts, supernova explosions, asteroid impacts, and solar flares. We inhabit a kind of cosmic firing range, and thus far, we have been remarkably fortunate. Over the 4 billion years that Earth has supported the development of complex life, no nearby magnetar has aimed a direct blast at us. No gamma-ray burst from a dying star has sterilized our planet's surface. We have managed to evade every potential catastrophe. But the question remains, how much longer can our luck possibly hold? The laws of probability suggest it should hold for a very long time. The galaxy is immense, and truly dangerous objects are comparatively rare. The likelihood of a cataclysmic event occurring in any given year is incredibly small. But when viewed across millions of years, those small probabilities begin to add up. Over billions of years, they approach certainty. At some point in the distant future, Earth's luck will run out, unless we are no longer here to witness it. The ultimate lesson that magnetars offer us may not be about magnetars at all. Instead, it might be about the critical importance of humanity becoming a multi-planetary species. As long as we remain confined to a single world, we are just one cosmic accident away from complete extinction. A magnetar flare, a large asteroid strike, any number of events could bring about our end. But if we can spread our presence across multiple star systems, then no single event would have the power to eliminate us entirely. Magnetars teach us that the universe functions on scales of energy and size that are far beyond our everyday comprehension. Objects exist that can unleash more power in a single second than our entire civilization has used throughout its history. Forces exist that make our most advanced technology seem like little more than children's toys. And these objects, these forces, are not rare anomalies. They are a standard feature of the cosmic landscape. Every time we observe a magnetar, every time we detect a fast radio burst, we are given a profound reminder of our place in the grand scheme of things. We are small. We are temporary. We live in a universe that creates and destroys on timescales and physical scales that dwarf all of human experience. Stars explode. Black holes collide. Magnetic fields can twist space into knots. And amid all this, life clings to tiny, rocky worlds, hoping that the chaos will pass it by. Yet, a paradox emerges from this picture. That same violent universe is what created us. The heavy elements that make up our bodies were forged in the heart of stellar explosions. The energy that sustains life on our planet comes from a star. The magnetic field that protects Earth is generated by a molten core, a small-scale version of the same physics that powers a magnetar. We are, in a very real sense, made from cosmic violence. Our existence is a consequence of it. Magnetars are not glitches in reality. They are reality displaying its full dynamic range. The universe can be gentle, allowing planets like Earth to orbit stable stars for billions of years. But it can also be catastrophically violent, giving rise to objects that bend and break every physical law we once thought was absolute. And perhaps that is how it must be. Perhaps the cosmos requires both. The quiet regions where life can slowly emerge, and the violent regions that forge the very elements that life requires. It is a balance between creation and destruction, played out across the expanse of cosmic time. We find ourselves here, now, in this moment, on this planet, looking up at a sky filled with both wonders and terrors. Magnetars pulse in the darkness, invisible to our eyes but blazing brightly in X-rays. They remind us that the universe is larger, stranger, and more perilous than we can ever fully grasp. But they also remind us of our own capacity for understanding. We have successfully detected these objects, measured their properties, and constructed theories that can explain their behavior. We have taken one of the most extreme phenomena that nature can produce and transformed it into a field of science. That in itself is a remarkable achievement. It says something profound about what the human mind is capable of. So, while it is true that magnetars are terrifying objects of pure extremity that push every physical law to its breaking point and can destroy worlds from light years away, they are also a testament to our own quest for knowledge. The energy scales on which magnetars operate are so immense, they make ordinary stars seem faint by comparison. In these objects, we see a representation of everything that makes the cosmos hostile to life. Yet they also encapsulate so much of what makes space profoundly beautiful. They are the universe pushed to its absolute boundary, a place where the laws of physics are strained to their breaking point, yet somehow manage to cohere. The reality they reveal is stranger, more intense, and ultimately more magnificent than anything we could possibly imagine. This is the essential nature of a magnetar. They are not simply cosmic behemoths that defy all known principles. Instead, they serve as evidence that the principles themselves are far more adaptable, more severe, and more astonishing than we had ever conceived. They are a demonstration from the universe of what becomes possible when matter, energy, and magnetic fields are compressed until something fundamental must yield. And in the end, nothing truly yields. Instead, everything is transformed. The space surrounding a magnetar is anything but empty. It is instead filled with unseen forces that extend for thousands of miles, exerting their influence on any object that ventures too close. These forces do not merely pull with gravity. They also push, twist, and accelerate matter through the power of pure magnetism. For any object that could manage to survive long enough to enter into orbit, that orbit would become a physical nightmare. Conventional orbits adhere to straightforward rules. An object's forward velocity is balanced by the inward pull of gravity, a relationship that creates a stable ellipse. This is how planets orbit stars, and moons orbit planets. The mathematics are elegant and predictable, first outlined by Newton over 300 years ago and later refined by Einstein. Close to a magnetar, however, those elegant equations simply break down, crushed by the overwhelming presence of extreme magnetism. Consider what would unfold for a hypothetical asteroid that somehow managed to survive in an orbit 1,000 miles from a magnetar. While gravity would attempt to keep it on a steady course, the magnetic field would constantly interfere. Since most asteroids contain elements like iron or nickel, the field would pull on the object, but not in a uniform way. Different sections of the asteroid would feel different magnetic pulls based on their specific composition and alignment. This non-uniform force generates torque, causing the asteroid to begin tumbling. Its rotation would soon become chaotic and entirely unpredictable. This tumbling, in turn, alters how the magnetic forces affect it, at times accelerating it, and at other times slowing it down. The orbit itself becomes unstable. Within a matter of days or weeks, the asteroid would either be drawn inward to crash upon the magnetar's surface or be violently ejected into the void of interstellar space. And this scenario assumes the asteroid could even remain intact. At a distance of 1,000 miles, the magnetic field still possesses a strength greater than 1 billion Gauss. Any material with magnetic properties would be subjected to colossal internal stresses. Crystals of iron would be forced to align with the field, creating immense strain. If the asteroid contained any structural flaws or fractures, this magnetic stress would tear it to pieces. The single asteroid would become a diffuse cloud of fragments, with each piece charting its own erratic trajectory. Scientists who have modeled the appearance of a debris disk around a magnetar have arrived at an unsettling picture. Nothing is capable of maintaining a stable orbit. Matter is perpetually either falling into the magnetar or being cast out. Such a disk would be a fleeting, ephemeral feature, constantly being refilled by flares, ejecting material from the magnetar's surface and simultaneously being cleared away by the relentless magnetic forces. Any observer would witness a shimmering ring of doomed material, spiraling and fragmenting in real time. The question then arises whether a planet could survive in the vicinity of a magnetar, and the answer is almost certainly no. A planet near enough to be of interest would become tidally locked, with one hemisphere perpetually facing the magnetar. That side would endure a continuous bombardment of radiation and particle winds. Any atmosphere it might have possessed would be stripped away within a few years. The magnetar's field would induce powerful electrical currents within the planet's core and crust, generating so much internal heat that the surface would melt. Even at a much greater distance, perhaps millions of miles away where the field is weaker and radiation levels are more survivable, another problem persists. Magnetars do not release their energy in a steady stream. They are prone to unpredictable flares. A planet that had maintained a stable orbit for decades could be incinerated in an instant when the magnetar suddenly erupts. Any ecosystem that had miraculously evolved would be repeatedly sterilized, reset back to its starting point with each outburst. Yet, a truly perplexing detail emerges from this. Certain neutron stars, a category that might include dormant magnetars, are known to have planetary systems. Astronomers have detected them by observing tiny variations in the timing of radio pulses from pulsars, which are caused by orbiting bodies. These planets exist at distances of millions of miles, far enough to be safe from immediate annihilation. They are not the original planets that existed before the supernova. Rather, they formed from the debris disk left behind. This discovery confirms that planets are capable of forming around neutron stars. If they can form around standard neutron stars, it seems plausible they could also form around magnetars during a quiet phase, after the magnetic field has significantly weakened. Such worlds would be dark and frozen, bathed not in visible light but in X-rays. They would nonetheless exist, silent testaments to the violent events that brought them into being. And if planets can exist in such an environment, One wonders what else might endure out there. On the 26th of August 2008, astronomers observed a supernova in a nearby galaxy, NGC 641, located approximately 13 million light-years from Earth. It was given the designation SN 208D. Initially, it seemed to be a typical event, a massive star exploding, shining brightly, and then starting its gradual decline. Following standard procedure, telescopes monitored it for weeks, but this particular supernova did not fade as expected. After its initial drop in brightness, it began to brighten once more. It then remained intensely bright, holding that luminosity for far too long. Something inside the expanding cloud of debris was injecting energy into it, causing it to glow as if it had a secret power source. Scientists worked urgently to understand what they were observing. Through careful analysis of the light spectrum and total energy output, the answer became apparent. A magnetar had been born inside the explosion. This was not just any magnetar. It was one of the most energetic and rapidly spinning objects ever found. It was rotating at a rate of roughly 1,000 times per second, so fast that its equator was moving at 20% of the speed of light. This particular magnetar was a newborn, possibly only hours old at the moment of its first detection. As it rotated, its colossal magnetic field functioned like a brake, causing it to slow down through a process known as magnetic dipole radiation. Its enormous rotational energy was converted into electromagnetic radiation. This radiation then heated the surrounding supernova debris from the inside out, making the entire remnant glow far brighter than it should have. When scientists calculated the figures, the results were staggering. In a single day, the magnetar was releasing more energy than our own sun does in 100,000 years. All of this power was derived from its slowing rotation. The object was, in effect, spinning itself to death, pouring its rotational energy out into space through its magnetic field, and humanity was witnessing this process as it happened. This discovery served as a powerful confirmation of the leading theories about how magnetars are born. It was long theorized that young magnetars rotate at incredible velocities, but scientists had never witnessed one in the immediate aftermath of its formation. The supernova SN208D provided that unprecedented opportunity, a front-row seat to a cosmic birth. With every observation, new layers of detail came into focus. By measuring how quickly its spin was slowing, astronomers could deduce the strength of its magnetic field. The object's brightness was a clear indicator of its energy output, while its spectrum revealed the composition of the surrounding material. For years afterward, the astronomical community kept a watchful eye on the event. The remnant of the supernova steadily dimmed as the magnetar itself began to lose momentum. Its period of rotation lengthened, increasing from just 1 millisecond to several. Correspondingly, its energy output declined. Yet even as it slowed, the magnetar remained a beacon of immense power, continuing to outshine thousands of ordinary stars. Then, approximately 3 years after its formation, a distinct change occurred. The magnetar produced its first detected flare, a sudden, brief surge in X-ray emissions that was recorded by multiple satellites. This behavior was not unexpected. Young magnetars are inherently unstable objects, their crusts still in the process of forming and settling into a final state. In these early years, starquakes are thought to be common. The flare served as confirmation that this object was truly a magnetar, ruling out other, more exotic possibilities. What made this entire series of observations so revolutionary, however, was its completeness. Never before had a magnetar been tracked from the moment of its creation. Every other magnetar known to science was already years, decades, or even centuries old when it was first discovered, offering only a glimpse into its middle or later life. SN208D presented the full narrative, right from the beginning. The resulting data showed that magnetars do not emerge at their maximum strength. Instead, Their magnetic fields appear to build up over time as the interior of the star settles and its internal currents align. This suggests the very youngest magnetars might possess fields that are weaker than their eventual peak values. They intensify during their first few years, reach a maximum intensity, and only then begin a long, slow process of decay. The experience is akin to watching a star being born, but compressed into a timescale that is actually observable for humans. This young magnetar also helped resolve certain questions about the diversity of supernovas. For some time, astronomers had been mystified by exceptionally bright supernovas that did not conform to standard models. Now, there was a compelling explanation. Some of these events were being powered by a magnetar. The newborn object functions like a cosmic battery, taking the rotational energy from its own spin and releasing it as powerful radiation. This injection of extra energy can make the supernova appear superluminous, potentially hundreds of times brighter than normal. Since that discovery, more examples have been identified supernovas that remain bright for an unusually long time and exhibit the telltale signs of a central engine pumping energy into the expanding debris. Each new case provides more insight into how magnetars form and evolve during their critical first months. But these observations have also led to a sobering realization. We are only able to witness this process in detail if the supernova occurs in our relative cosmic neighborhood within a few 100 million light years. At greater distances, the crucial details become blurred, and the signature of the magnetar can be missed entirely. This implies that across the vastness of the universe, there could be hundreds or even thousands of young magnetars being born every year, with humanity only able to see the very closest ones. Each birth is its own cosmic drama. A massive star ends its life, its core collapses, and for a fleeting moment, a magnetar spinning 1,000 times per second blazes into existence. On the 17th of August 2017, gravitational wave detectors registered a truly extraordinary event. Two neutron stars, which had been locked in a spiraling dance for billions of years, finally collided. The merger took place in a galaxy 130 million light-years from Earth, and telescopes all over the world quickly turned to observe it. What they witnessed would forever change the field of astronomy. The collision generated gravitational waves that rippled through space-time itself. It ignited a kilonova, a type of explosion fueled by the radioactive decay of heavy elements. It also broadcast gamma rays, X-rays, and radio waves, virtually every form of radiation that can be detected. These observations validated decades of theoretical work on the outcomes of neutron star mergers. But the event also raises a haunting question for scientists. What might happen if one of those merging neutron stars was a magnetar? What if, instead of two conventional neutron stars meeting, a magnetar were to collide with its companion? No one has yet observed such an event, but the theoretical predictions describe a scenario of almost unimaginable extremity. It would begin during the final approach. As two neutron stars spiral toward each other, they radiate gravitational waves, which carry away orbital energy and cause them to fall closer. This is standard physics, confirmed by direct observation. A magnetar, however, introduces profound complications. Its magnetic field extends for thousands of miles. As the companion neutron star passes through this field, it is subjected to enormous magnetic forces. Since all neutron stars possess their own magnetic fields, the two fields would interact, attracting or repelling each other depending on their alignment. The orbit would become unstable. Rather than a smooth, predictable spiral, the neutron stars might experience sudden bursts of acceleration or deceleration as their magnetic fields lock together and then break apart. The resulting gravitational wave signal would show clear irregularities, stutters, in its otherwise smooth frequency sweep. This magnetic interaction would also heat both objects. Currents induced in their crusts by moving through each other's fields would generate immense thermal energy, causing their surfaces to glow more brightly. It's even possible that material could be ejected by magnetic pressure before the actual collision. Such pre-merger emissions would be a unique signature, alerting observers that a magnetar was involved. Then, the collision itself would occur. The impact would last for mere milliseconds. Two spheres of ultra-dense matter, each about 12 miles across, would slam into one another at a significant fraction of the speed of light. The release of energy would be inconceivable, with temperatures soaring into the trillions of degrees. The magnetic fields would be compressed, reaching strengths thought to be impossible even for a magnetar. In those few milliseconds, several outcomes are possible. If the total mass of the merged object is below the maximum limit for a neutron star, roughly 2.4 to 3 times the mass of our Sun, it might temporarily survive as a hypermassive neutron star. This object would be unstable and spinning at a fantastic rate, but it would not immediately collapse. This hypermassive remnant would possess a magnetic field born from the merger of two others. If one of those was a magnetar's field, the result could be a field even more powerful than either of the originals. For a few seconds or minutes, the universe would host the strongest magnetic field ever created. One so intense, it could directly influence the geometry of space-time. But this state cannot last. The hypermassive neutron star is supported against gravity only by its rapid rotation. As it radiates away energy in the form of gravitational waves and electromagnetic radiation, it slows down. Its centrifugal support weakens. Gravity wins. The object collapses into a black hole. This collapse is incredibly swift. In less than a second, a 12-mile sphere of magnetar material becomes a singularity, hidden behind an event horizon. The magnetic field, however, does not vanish in an instant. This material becomes frozen into the matter that remains outside the event horizon, forming an accretion disk of debris. Such a magnetized disk has the power to launch jets, which are focused streams of particles and radiation that erupt outward along the axis of rotation. These jets may provide an explanation for some gamma-ray bursts. The brief flashes that last for less than 2 seconds are known to originate from neutron star mergers, yet some are more luminous than others. A number of these events display features in their spectra that are not predicted by standard merger models. The presence of a magnetar as one of the neutron stars with its powerful magnetic field could account for these anomalies. Matter that is thrown out during the merger carries the magnetic field along with it. This magnetized ejector behaves in a way that is distinct from the material expelled in a typical merger. The field contains the matter, directs its flow, and imposes a structure upon it. As a result, the kilonova that ensues might be asymmetrical, shining more brightly in certain directions. Observers viewing it from different angles would perceive varying levels of brightness and color. A definitive observation of a magnetar-neutron star merger has not yet occurred. Statistically, such an event is expected to be uncommon. Magnetars maintain their active phase for only about 10,000 years. The likelihood of witnessing one in that brief window as it merges is quite low. Still, the universe is immense, and somewhere, at some point, it must happen. When we finally register such an event, with gravitational wave observatories alerting us and telescopes capturing the display of light, we will see something truly unprecedented. It will be the merger of one extreme object with another, even more extreme. This collision would momentarily forge the most powerful magnetic field that the cosmos is capable of creating. In the desert landscape of South Africa, a vast collection of antennas is oriented toward the sky. This is Meerkat, one of the most sensitive radio telescope arrays ever assembled. Its 64 dishes function in unison, combining their signals to perceive phenomena that no single telescope could possibly resolve. Among its numerous objectives, it is searching for something very particular: the faint whispers that occur between a magnetar's flares. The majority of magnetar observations concentrate on the most dramatic occurrences. These include the giant flares and X-ray bursts, events that illuminate detectors all across the electromagnetic spectrum. But in the intervals between these violent outbursts, magnetars are not entirely silent. They produce a steady stream of radio waves, which are weak but can be detected if one knows where to aim and how to listen. These radio emissions are different from the bursts associated with flares. They are persistent, a constant presence that pulses in time with the magnetar's rotational period. Scientists refer to this as quiescent radio emission. The term itself can be misleading, as there is nothing truly quiet about a magnetar. But when set against a giant flare, this signal is merely a whisper. Meerkat is exceptionally good at detecting such whispers. Its dishes are distributed over 5 miles of the South African terrain. By working together, they form a virtual telescope of extraordinary sensitivity and resolution. It is capable of detecting radio signals that are thousands of times fainter than what previous telescopes could manage. The array is leveraging this power to conduct a systematic survey of all known magnetars. The findings have been surprising. Some magnetars, once believed to be radio quiet, are in fact emitting faint yet steady radio pulses. Others exhibit variability, with their radio brightness fluctuating over days or weeks without any related X-ray activity. A select few display polarization patterns that are revealing the structure of their magnetic fields with unparalleled detail. But Meerkat has uncovered something even more fascinating: microflares. These are minuscule bursts of radio emission that last for just milliseconds and happen at random intervals between the major flares. Each microflare unleashes only a tiny fraction of a giant flare's energy, but they occur with high frequency, sometimes dozens in a single day, and they are providing scientists with crucial information about magnetar magnetospheres. The magnetosphere is the area surrounding a magnetar that is dominated by its magnetic field. Charged particles become ensnared there, spiraling along the field lines. This magnetosphere extends for hundreds of miles from the surface, an invisible but perpetually active region. It appears these microflares are triggered by small-scale magnetic reconnection events within this zone. The process is similar to lightning. In a thunderstorm, charge separation builds up. Eventually, the electric field grows strong enough to ionize the air, which results in a lightning bolt. Magnetar magnetospheres operate on a similar principle. Stresses accumulate within the magnetic field. The field lines become twisted. Ultimately, a small area can become unstable and reconnect, releasing a burst of energy in the form of a microflare. Through the study of thousands of these microflares, scientists are constructing detailed maps of magnetar magnetospheres. Every flare provides information about the field strength, its geometry, and the plasma density at the specific location where it happened. The method is analogous to tomography, where a three-dimensional image is built from numerous individual data points. This research is showing that magnetar magnetic fields are substantially more complex than early models had proposed. They are not simple dipoles with distinct north and south poles. Instead, they are twisted and knotted, featuring multiple active regions. Certain areas are comparatively stable, while others are in a constant state of reconnection. The field is a dynamic entity, evolving over timescales that range from days to weeks. Meerkat is also hunting for something that theory predicts, but that has not yet been confirmed: magnetar precession. If a magnetar's magnetic axis is not aligned with its rotational axis, the object ought to wobble, much like a spinning top. This wobble would manifest in the radio data as periodic variations in the arrival times and intensity of the pulses. Discovering precession would be a revolutionary achievement. It would inform us about the internal structure of the magnetar and how its mass is distributed. It might disclose whether the core is a superfluid, whether the magnetic field permeates the entire object, or whether currents are flowing between the crust and the core. All this could be learned from carefully monitoring the radio signal over months or years. A more profound objective, however, drives this research. Scientists are eager to understand how magnetars eventually cease their activity. What unfolds in their final years before they become dormant? Does the radio emission stop abruptly, or does it fade away gradually? Do the microflares become less common, or do they persist until the very end? To answer these questions, long-term monitoring is essential. Meerkat is capable of this task. It can observe the same magnetars month after month, year after year, constructing a timeline of their decline. With the next generation of telescopes coming online, such as the square-kilometer array, which will be 50 times more sensitive, we will be able to track even the faintest of these whispers. The ultimate goal is to catch a magnetar in the process of dying to witness the transition from an active to a dormant state in real time. No one has accomplished this yet, but with instruments like Meerkat keeping watch, we may finally observe the end of a magnetar's violent reign. A particular scenario lingers in the thoughts of astronomers, a concept that, while improbable, remains within the realm of possibility. It concerns a discovery that would compel a complete re-evaluation of our knowledge of magnetars and perhaps of physics as we know it. Some scientists suspect we might be drawing near to such a finding. Consider this hypothetical situation. A radio telescope captures a signal. This is not random static, nor is it an instrumental glitch. It is a distinct pattern, repeating at perfectly regular intervals. The pattern itself is intricate, possessing a complexity that seems to defy natural origins. It demonstrates structure, organization, and apparent information, and its source is a magnetar. The immediate reaction from the scientific community would surely be one of profound skepticism. Instruments are known to malfunction, and interference is a constant issue. Illusory patterns can emerge from noise that are not actually present. The human brain is inherently designed to perceive order even in randomness. Every researcher would therefore assume the signal was an error. They would proceed to check and recheck their data. The entire analysis would be run again. Different observatories would point their telescopes at the same target. If all of them observed the very same thing, and if that pattern persisted, then the serious questions would start to form. Could magnetars generate such organized signals through natural means? Based on our current understanding of physics, the answer is most likely no. The emissions from a magnetar are governed by the dynamics of its magnetic field, plasma physics, and the acceleration of particles. These processes are capable of creating pulses, bursts, and even periodic fluctuations. However, complex patterns that contain informational content would seem to require something else entirely. Such a signal would imply a level of organization that nature does not typically produce on its own. This holds true unless our fundamental assumptions about what is possible are incorrect. Perhaps magnetar physics, when pushed to its most extreme limits, can give rise to structures and phenomena that appear artificial but are not. It could be that specific magnetic field configurations are able to create resonant cavities that amplify certain frequencies. Maybe plasma instabilities can self-organize into patterns that repeat with an uncanny precision. It is conceivable that we are on the verge of discovering a new domain of physics, one where complexity emerges spontaneously out of chaos. Or there is another, more speculative possibility, that someone is not creating magnetars, but using them. We ourselves cannot create these objects, but harnessing their immense energy, modulating their emissions, could transform a natural cosmic body into a transmitter powerful enough to broadcast signals across the galaxy. The energy demands for interstellar communication are simply enormous. A transmitter would need to be so powerful that its signal could still be detected across thousands of light years. Our own most powerful radio transmitters struggle to reach even the closest stars before their signals fade into background noise. A magnetar, by contrast, can release more energy in a few seconds than our entire civilization has generated throughout all of human history. If an intelligence could tap into even a small fraction of that power and modulate it, they would possess the ultimate galactic transmitter. This idea has been explored in science fiction. Authors have imagined advanced civilizations employing stars as beacons, but magnetars are a more logical choice for such a purpose. They are brighter at the relevant wavelengths. Their emissions are already pulsed, which would make them simpler to modulate. And they are sufficiently rare that an advanced civilization might find and claim one for its own use. It is important to state that no credible scientist believes we have found such a signal yet. The fast radio bursts and other repeating sources we have detected all seem to be natural phenomena. The patterns observed so far are consistent with known magnetar physics. There is currently no reason to invoke intelligence as an explanation. Nevertheless, the possibility remains. As our telescopes grow more sensitive and as we study more magnetars in ever greater detail, we may one day find something that is anomalous. What would we do if we made such a discovery? The established protocols are not entirely clear. Science has rigorous procedures for confirming new findings. One must replicate the results, submit them for peer review, and systematically rule out all alternative explanations. But what happens if the alternative explanations are exhausted? What if every known natural process is considered and eliminated, yet the signal remains unexplained? The implications of such a moment would be staggering. It would signify that we are not alone in the cosmos. It would mean that intelligence exists at a level capable of manipulating the fabric of neutron stars. It would suggest that the universe is home to civilizations so far beyond our own that we are like ants attempting to grasp the principles of nuclear physics. And it would imply they are out there, perhaps observing, perhaps waiting. There is, however, another possibility, one that is equally unsettling. What if we discovered evidence of magnetar engineering that was ancient? What if we detected patterns in a magnetar's emissions that were clearly artificial but had not changed for millions of years? This would suggest that the civilization that created them is gone, long dead and extinct, leaving behind only their cosmic monuments in the form of modulated stellar corpses. That scenario would carry its own profound warning. If a civilization advanced enough to harness the power of magnetars can disappear, what does that say about our own chances for survival? What was it that ended them? Was it conflict, ecological collapse, or a cosmic catastrophe they could not prevent despite their incredible technology? Or did they simply transcend, uploading their consciousness into virtual realms and leaving the physical universe behind? We would be left staring at an answer we could not hope to interpret. These are the kinds of thoughts that motivate some researchers to continue the search. It is not because they truly expect to find something. The universe is immense, and the odds are astronomical. It is because the alternative of not searching seems worse. If there is even a 1 in a million chance that magnetars are being utilized, that intelligence has interacted with these objects, then we have a need to know. And so, the telescopes keep watch. Meerkat in South Africa, FAST in China, the Very Large Array in New Mexico, and dozens of others are all gathering data. They are analyzing signals from magnetars and other neutron stars, hunting for patterns, searching for anomalies, looking for anything that does not fit our current models. In all likelihood, they will find nothing. Magnetars will remain what we believe them to be: natural objects, extreme but ultimately comprehensible. They are the universe displaying its raw power, without any inherent purpose or meaning. But the search goes on. The day we cease to look is the day we resign ourselves to being alone, to the idea that intelligence is a rare and fleeting thing, and that the universe is merely physics playing out across time and space, with no one but us to witness it. Perhaps we are not yet ready to accept that conclusion.